Good morning, everyone. I know you're all having fun. Thank you for showing up early in the morning for this session. Um, yeah, so maybe one small correction in the introduction from going from quarter professor to half professor. I'm a full professor now. So if at all, no, that's okay. If at all that matters, that's okay. Yeah. So simply saying, yeah, simply joking. That's all. Yeah. Great. Okay. So I know it's a small group, so we can keep it informal and have it more interaction based and I was about to bring that up. Yeah, that was the next thing I wanted to bring that up. So yeah, maybe that was the exact question I wanted. So just how many of you have done deep learning before? Okay, and how many of you did the deep learning for computer vision as part of this course? Okay, and how many of you don't know what deep learning is? I mean, you probably know it, but you have not taken a technical course. Okay, okay, so there's a whole mix here. Okay. Okay, so then I'll try to keep this talk at a high level. Okay, let me also ask you one more question, right? So before we get into the talk itself, uh, how many of you want to go into the math and how many of you want to stay a little bit more high level? Okay, how many of you for more math? Okay, and how many of you a little bit more high level? All right, okay, it's a mix in every sense. So I think I've actually tried to make slides that can probably do a bit of both. Okay, so let's see, we'll see how things go. If required, I can skip a few slides, spend more time on a few slides, so on and so forth. So let me get into the topic for today's session, which is toward learning via explanations. So I would say it's a slightly more research heavy talk, right, rather than a tutorial heavy talk. Probably also with some sense of directions for the future for the field and so on and so forth, right? So the first half of the talk, I realized that there could be a mix. I did get to know that they're also just diploma students and so on. So the first half of the talk, I'll probably talk a little bit more about uh, how the space has evolved over the last decade and what we think the space may portend going into the future, right? So what can history tell us about where this entire space is going in the next few years? And then the second half of the talk, I'll probably go deeper technical, right? So I'll probably talk about some of the specific papers and go, that'll have more equations. Bear with me if at any point something becomes heavy, let me know. And please do feel free to ask questions. I think you're a small group. Just ask questions. I'm very, very happy to keep this informal, as useful as possible. Uh, okay, so maybe before, just to give a quick background about myself and why I'm talking about what I'm talking today. Broadly, the group I lead at IIT Hyderabad, our overall thesis is towards robust and reliable machine learning models in evolving environments. So that's what our overall thesis of our research is. And within this, there are a few dimensions that we try to explore. One is about making research more trustworthy, where we've been looking at broadly around explainability of AI models, deep learning models is something we've been focusing on. Because second dimension has been about making these models more robust in practice. If you've heard of adversarial robustness, we've also dealt with attributional robustness, geometric robustness, so on and so forth. Also talked about, we've been looking a lot into how do these models evolve with time, right? So the success of machine learning over the last decade plus is supervised learning, right? So where you take a large amount of labeled curated data, we know that we can train a model, right? You have to do a lot of engineering, but we know we can train a model. But now what if new classes come? What if at that point you don't have access to the data from the past? All of that become important considerations. So that's what we do with evolving with time. We do continual learning, open set learning, open world learning, some applications in that space. And we've also been looking at how do you work in settings which are data deficient and label deficient, right? So where you may not have enough data, where you may not have enough labels, but you still have to learn. Right? So obviously, as you can see, these are all research directions. I don't think we have technologies that can be straight away go to production or things like that at this point. Some of which we have, but some of which is still in research phase, right? But those are the different things that we look at in our group. And for the rest of the talk today, I'm probably going to focus on one aspect of our research, which is about making these models more trustworthy, right? Even within that, I'll focus on one specific thing, but I'll go to that a little later, right? But I'm happy to answer or discuss with any of you about other dimensions, but I'm going to focus on, if I had to be very specific, I'm going to focus on one bullet point there, which is causal XAI, right? So causal explainability is what I'm going to focus on, but I'll do that in the second half of the talk, right? So I'm probably going to be a little high level, very high level actually, in the first half of the talk. Okay, so as I said, I mean the first half will probably be about just understanding where the field has come and what opportunities exist, right, for the field as we go forward. I know that, I mean, in some sense, I think this is a very opportune time because many of you are completing a degree at this point in time, and what should you do next, right, is a pretty valid question to ask in today's times. What do you all think, right? So let me keep this more interactive. What do you all think, right? So what do you think in the next 3 years from now? What do you think are the kind of, let's keep it to AI, right? So that's the focus of today's session. AI and data science more broadly speaking. What do you think everybody will be working on 2 to 3 years from now? Any idea? Obviously, I mean, ChatGPT, LLMs, Sora have revolutionized how things are going. But the obvious question then is, what do we do, right? Next 2, 3 years, right? Is it all done? What do we do? Yeah.
So for healthcare domain, explainability and interpretability becomes a very, very integral part because developing a model is easy. Like you said, you already covered the diversity and the mistakes it can have when you generalize it to another setting. So, and also to improve trust among the end users. In healthcare, the end users are two types. One is the doctors themselves and also the patients. So both of them need to develop that trust. So explainability would be a large part of building the trust. So I, at least in this domain, I feel a lot of work will go on to these explainability part of AI. We would want to understand what's going on inside the black box. And I believe that even in other fields, a similar drive will be there. Because anywhere you want to deploy, you want that trust, especially with all these problems with hallucinations in generative AI and things like that. Accuracy becomes, and explainability becomes more important probably than just accuracy. Yeah, thank you.
Got it. Yeah. I mean, I completely agree. And but yeah, I think that there have been, in fact, the last year or so, there has been a lot of discussions on, can LLMs reason, right? So can ChatGPT reason? It's, I think, philosophical debate, right? So somebody could say, if you actually give it an arithmetic problem, it can work out every step and give you the answer. So now what do you think? Does it reason or not? Is a philosophical debate, right? Because one could say it's giving me every step, it's reasoning. Somebody could say that even that is memorized, right? So it's not reasoning, right? So that's a philosophical debate that we'll keep it for later. But any other thoughts, right? Any other thoughts on what do you think? Maybe you want to speak into the mic if you don't mind.
I think we should move forward to building AGI.
AGI, okay,
means,
all right.
It should be our focus. So after hype in LLM, we should build robots that has general capability of doing any task, human task, and so that should be
got
cool.
it. Okay, I'll touch upon that too. I mean, I will say a few provocative things as we go, right? So, but I completely agree, though. I completely agree. Okay. Any other thoughts? Feel free to share. It's a small audience anyway.
I would like to work ML learning with farmers.
Learning with farmers.
Farmers.
Okay. So agriculture, you're saying.
Agriculture.
All right. Okay. Got it. Okay.
I am from farmers' sons.
Background. Okay. I see. Okay. Got it. Okay. Okay. Any other thoughts? Okay. We'll pause a little later again, right? So feel free to interject again and ask questions. I'll come back to some of these thoughts a little later. I completely agree with things like robotics as we go forward, but I'll share with you my perspective as to why I think those could be important things as we go. So let's just zoom out a bit, right? So as I said, the first half hour or so is going to be very, very high level. I'm not going into any equation, very, very high level. I just thought that since many of you are graduating, and at least from what I've spoken to, many of you have aspirations to do research. And a big question in AI research today is, what is there for me to do? ChatGPT writes papers. ChatGPT almost can tell you what to do next. What is there for a student to do is a pretty big problem at this point in time. Okay, so I don't know if any of you attended yesterday's workshops too. I think there was one on safety and responsible AI, if I'm right. Right? Okay. So I mean, the obvious question to ask is it all good? Firstly, right? So there's tremendous progress, but is it all good? Is a valid question to ask. And not really the case. I won't get into too much of this today, but I know that yesterday was sessions on responsible AI. There have been issues of say bias in face recognition technology. I'm not sure how many of you know, but the bias is to the extent that there have been innocent people who have gone to jail for a few years because of technology being applied on face recognition, right? So it's extreme in terms of its implications. We obviously know about deepfake videos. It's been all around the news. Many of you may have heard of deepfake voices too. I think there's a lot of news going around that. And the entire threat landscape is pretty wide at this point in time as to the risks around AI, right? And that has led to this entire conversation around responsible AI. How do you use AI in a responsible manner? Because AI can have many other fallouts. I think every revolutionary technology has had its fallouts, right? Going back to dynamite of Alfred Nobel, right? But then we have to see how to use that in a responsible way. And this has led to a lot of conversation around topics like fairness, robustness, accountability, privacy, reliability, and of course explainability, right? Which, so just to put these things into perspective, we are going to talk about one facet of responsible AI today. You probably saw a couple of facets in yesterday's workshop for those of you who attended it. Okay, but today we're going to see one facet, which is explainability. I think responsible AI is far broader than that. There's also robustness, there's accountability, there's fairness, right? How do you make models fair? Right? So suppose you're using ML to decide who should get 10 rupee per kg rice, right, in the country. Right? How fair should it be? Right? So it's a very, very important, and we are already talking about using ML for those kind of things, right? How do you use it for urban governance? But how do you talk about fairness of models? These are very algorithmic areas, in fact. In fact, fairness of AI is a very theoretical area, right? People talk about what do you mean by fairness? How can you guarantee fairness from a theoretical perspective, so on and so forth, right? So it's rich in terms of contributing from a research perspective. Broadly speaking, responsible AI is the ethical design, development, deployment and management of AI systems, and there are many dimensions to this, right? But let me again zoom out a bit and let's just see the history of deep learning itself, right? I hope you'll all agree with me that the significant success in AI over the last decade has been deep learning, right? So bear with me if I say AI, deep learning, machine learning in the same breath. I'm using that in common parlance, but technically speaking, I hope all of you are aware that AI is a superset, ML is a subset, DL is a subset of ML, right? So DL is just one small space, but it's like, I mean, in any area, if one algorithm performs the best, that becomes like a synonym for the entire area, right? So that's what has happened. So I may use it in the same breath, but keep in mind that they are different things. So the history of deep learning is very, very vast, right? So in fact, this is not the first wave of deep learning, right? So let's go back in time and see that. The earliest efforts were way back in the 1940s when McCulloch and Pitts wanted to come up with a computational model of the neuron, which was called as the electronic brain project. And that is the computational model we use to this day, right? To this day, that's what we end up using. Then in towards the 50s, there was a wave actually on trying to make neural networks popular. In fact, the word AI was coined in 1955. I'm not sure how many of you have heard the history, in a conference called the Dartmouth Conference, where a bunch of people came and coined the word AI, and the way it was coined, it was in fact not even the first option. They coined it because they thought it would allow them to get funding. They thought it was like very fancy and it would allow them to get a lot of funding for that particular research. So the first wave of AI in deep learning was actually in the 1950s. Okay, that's when the first wave of AI went. And people started working on neural networks at that point in time, but everything was in hardware. Right? A room like this would host one perceptron, right, or one neural network. It was all in hardware at that point in time. Then they also came up at that point, and learning rules as to how do you set the weights for each of these also came up at that point in time, right? So the pretty much the basics of our learning rules for neural networks today came at that time. They came in the late 50s and 1960s. The data learning rule is largely what we use for the final layer, right? The in-between intermediate layers of a neural network have changed since then. So that was called the late 50s to 70 was actually called, about the late 60s, was actually called the first golden age of neural networks. A lot of people started putting their efforts on it. I'm not sure how many of you know this history, but in 1966, a few professors from MIT decided to have a summer internship project to solve computer vision. Right, to solve computer vision, right? It was supposed to be a 3-month project to solve computer vision at that point in time. And obviously they realized at the end of the summer internship that it's not a summer internship, okay, it's going to take, and we still not solved the problem to this day at this point in time. But what also happened at that point in time is, many of you may have heard of the XOR problem for neural networks, which is Rosenblatt, who came up with the perceptron at that point in time, claimed that a perceptron could classify any kind of data, right? That's the claim that he made, okay? Very soon, Minsky and Papert, a couple of faculty from MIT, came up with this XOR problem and said that a perceptron is a linear classifier. Okay? Any linear classifier cannot solve the XOR problem. Okay? You can see here that you need a non-linear classifier to solve the XOR problem, and that again brought back neural networks and deep learning to an earlier time, and that's called as the dark age of deep learning, right? But in the 1970s and 80s is when another dimension of AI developed, which is called as symbolic AI, right? So logic and other aspects of AI started developing as alternate ways to achieve AI. I'll come back to why this is important a little later, right? As to in terms of what it tells us about the future, I'll come to it after some time. Again, the 80s was again like a rebirth. The neocognitron was one of the earliest efforts, similar to convolutional neural network, came in the early 80s. Then in 1986, the backpropagation algorithm, which we use to this day, came in 1986 by Rumelhart, Hinton and Williams. Then came convolutional neural networks in late 80s, early 90s. But once again, so that was the second upswing for neural networks, right? If you talk to a lot of people, even from India, who probably did their post-graduation around the late 80s and 90s, many of them will tell you that they worked on artificial neural networks for their thesis, right? You speak to many of them, this will be a uniform answer you'll get from many people who did their masters in India, right? Even in India, forget other countries, right? In late 80s, 90s. So that was the second upswing of deep learning and neural networks. But once again, people realized that nothing was practical, right? Whatever they showed, it was not really becoming commercially useful. They could not deploy it, make things relevant in practice, so on. And around the time came support vector machines and boosting, bagging, all of these other machine learning methods came and they became popular. And once again, neural networks went through what is called as their dark age at that point in time. In fact, it went to that point in time that if you had a neural network in a paper title, that paper won't get accepted to the conference. People just thought it just didn't make sense, right? Because you really don't know what's going on inside a neural network. So if you worked on neural networks, you pretty much won't get accepted at any conference in terms of your research. Right? That's how it was at that point in time. But then in 2006, Hinton again came up with this idea of what is called hierarchical feature learning. I mean, that was the thing that took off this wave, although later people realized that that was not really required. And of course, in 2012 came AlexNet, and that since 2012, I mean, many of you may have heard of 2012 being the end of the world in Mayan calendar or things like that. Okay, but there's something that definitely changed. Okay, deep learning took off at that point in time, right? So there was some world-changing event at that point in time if you go back and see 2012. Okay, so as I just mentioned, I think 2012 was the turning point when AlexNet solved the ImageNet challenge. And what was really big about it? What was really big about solving the challenge? Until then, most of the networks that were, most of the methods that were used for solving the ImageNet challenge, which was an image classification challenge, had error rates something like 25%. And like every year, error rates would come down by about 1%, 2%, and that was considered a big thing at that point, right? Then AlexNet came and brought the error rate down by 10%, and that was unheard of, and that really catapulted the success of deep learning. And since then, we don't need to talk about the success, but I'm just going to quickly summarize what has happened in the last 12 years, more to understand what could happen as we go forward, right? So from that perspective, as I said, bear with me for the first half, I'm going to keep it a little high level. So one thing that definitely happened after 2012, after the success of AlexNet, was deeper the merrier, right? So networks started getting deeper and deeper and deeper, right? AlexNet was 8 layers. 2013, 2014, a lot of people were still doing 8-layer networks. Then came VGG, which went up to 18, 21, things like that. Then came GoogleNet, okay, which went up to 21, 22 again. Then in 2015, 2016 came ResNets, which went up to 52, 104, so on and so forth. And this explosion of layers started happening, right? So that was definitely a trend that started happening, okay. People hybridizing architectures, right? Why do we use only a convolutional neural network or only use a recurrent neural network? Why don't we put them together to solve problems, right? So that also came up at that point in time, and people started putting these networks as different pieces together to solve more complex problems. Like video was an example, where if you put a CNN and an RNN together or an LSTM together, then you solve video level problems. I know that some of you probably have not done a deep learning course, so bear with me if I use these abbreviations, but it doesn't matter for the context of this conversation, right? So it's okay if you don't follow exactly what's going on. So the broad idea was, how do you mix and play all these different modules that were coming in such a way that everything is backpropagable end to end, right? So you can use backpropagation as the algorithm to do end to end, but you try to mix and match a lot of modules, right? So that's what came at that point in time. But 2018, 2019 is when transformers came into the picture. I hope some, even if people who have not done these courses, you've heard about it at least, right? So transformer architecture is what GPT stands for. The T in GPT stands for transformers. Okay, so transformer is an architecture that came in 2018-19. So you could look at the journey as a journey of settling on an architecture, right? So 2012 onwards, we realized that okay, deep learning can be successful. Started trying out various different architectures, started putting various architectures together, and finally came up with one architecture that seemed to solidify, right? So transformers was that change, and I think for the last 5-6 years we have probably stayed on that, right? We have stayed on transformers being the preferred architecture across different data. It started with NLP, natural language processing, then went into vision, went into speech. Now it's pretty much transformers across the board for all kinds of data at this point in time. Okay. And an obvious takeoff, right? I actually feel this is an understated reason for the success of deep learning and AI itself in general is, I mean, I would probably reiterate this a couple of times that this is understated, is the openness of the research and science in this field, right? Often people don't credit that for the success of AI in the last 10 years, but in my opinion, more than the models itself, the open science approach to doing research is what really changed things in the last 10 years. Why am I saying so? Archive came in these 10 years. If any of you, I hope all of you have heard about Archive. GitHub came in these 10 years, right? So people started putting out whatever they created the next day on Archive. People started putting out whatever code they created the next day on GitHub, right? Why was this important? Just circle back a little bit before 2012. The way research was done, right? So even during my PhD, the way research was done is you first, somebody writes a paper. Suppose they did a paper in 2020, right? You would get to know about that paper in 2021, okay? Because it would take 6 to 9 months for them to get accepted at a conference and present it. And only when you go to the conference, you will see the paper. Till then, you would not see the paper, right? And then after that, it will take you 6 months to implement that paper to see whether it works. It may not work, give you errors, you have to figure all of that out, right? And then you try to improve it. That's almost like 2 years gap between when they did it and when you did it, right? 1.5 to 2 years gap. That changed to 1 day, right? Which means if Google came up with a model yesterday, I could build upon that model today, right? That is massive in terms of the exponential growth of how this field went through in the last 10 years, right? So I feel this is often understated in terms of its contribution to how AI is developed over the last 10 years. But I think open science, open development of frameworks, people making frameworks open source everywhere, I think was a tremendous catalyst, understated catalyst in this space. And obviously there have been a lot of programming frameworks in this space too. I think we have settled down to TensorFlow and PyTorch at this point in time. But over the years, there have been several others that have competed for the space before we have settled down on TensorFlow and PyTorch. And obviously, once transformers clicked, the immediate leverage that the community came up with was the idea of generative pre-trained transformers, or what is called GPT. So from transformers, we went to generative pre-trained transformers. So even there, if you see the journey, in 2017-18 is when transformers came into the scene. 2018 is when BERT came into the scene. If any of you have done an NLP course, you may have heard of BERT embeddings. Then GPT-2 came in 2019, GPT-3 in 2020, GPT 3.5 in 2021, and of course, the rest of it is something that you've been hearing about in the news, right? So this entire generative pre-trained transformer revolution has been around for 5-6 years now, right? Although it's been more popular in the last couple of years. And the other thing that has happened in the last 10 years is historically deep learning, machine learning, and any of this space has always been a discriminative approach. Neural networks, if you can go back and recall your machine learning course, you may have heard of discriminative models and generative models, right? So SVMs, neural networks, they're all discriminative models, right? Naive-based classifiers, you could look at them as generative approaches, okay? Or Gaussian mixture models and so on. So, but one thing that changed is to go from discriminative to generative models. Why is that important? Because generative intelligence is higher than discriminative intelligence. Any kid can recognize a lion. How many kids can draw a lion? Right? Drawing something is always harder than just recognizing something. Right? So generative intelligence is a higher form of intelligence, just from a pure intelligence perspective. Take AI out, take deep learning out. Right? And that is something that the community started venturing out to, given the success of the discriminative models. Now, that's the brief overview of how things have evolved in the last 10 years, right? So, it's a very, very high level view, as I said, right? A 20,000 feet view. The thing that I wanted to spend a bit more time on is now, what does it tell us about where you should go from here, right? So as many of you being graduating, looking at opportunities for research, maybe looking at opportunities for startups, looking to see where you should invest your time, money, maybe, right? So what are the opportunities is something that I thought I should focus on. Maybe I'll do 10 minutes of that before we get into specifics. And a disclaimer here is that these are just my personal thoughts, right? So it's not that this is something that's documented somewhere or things like that. So I'm happy to debate, happy to take discussions here too. In terms of architectures, right? So obviously there has been an explosion of architectures, right? We started with convolutional neural networks, recurrent neural networks, went to transformers, went to variations in transformers, so on and so forth. But the question here is this really sustainable, right? All of this is all right for web scale problems, right? The kind of problems that ChatGPT is deployed for today. But if I want to run something in my organization, do I need ChatGPT? Do I need that scale of an LLM with billions of parameters? We are talking about hitting 1 trillion parameters now, right, in some of these models. Do you really need something like that? Is a question to ask, is a question to probably dial back and see what do we really need. And that has led, I'm not sure how many of you have heard about, how many of you know what SLMs are? Anyone heard about SLMs? Small language models, right? LLMs are large language models. Phi came recently, right? There are a few others too, right? So, yeah, there are a few others too. Small language models are coming up now to see whether you really don't need very large models. Maybe you can achieve the same thing using smaller models, or at least distill large models into small models. Right? That's one aspect that's definitely developing. But there's a larger dimension to this, which again I don't see people talking about more. Is I'm not sure how many of you know the carbon footprint angle to all of this, right? There was a very nice paper in 2018, right? And 2018, I hope you agree with me, is quite old, right? So things have significantly exploded since then. But even then, there was this very nice graphic where they showed to train one BERT model, right, which is an NLP model. Please do stop me and tell me if I use an abbreviation that you don't understand. Please stop me and ask what is that, right? So I'm assuming a few things in the background here. But when they used an NLP model, they showed that the carbon footprint used to train one NLP model from scratch was equivalent to the carbon footprint of the lifetimes of 5 cars. That's what they showed here. You can look at it right here. If you're in the graphic, you can see the numbers here. Okay, so a US car is 126,000 lbs of CO2, and a transformer architecture with neural architecture search took 625,000 plus, 5 times the carbon footprint of 5 cars lifetimes, right? So just dial back and see this. On one hand, we are talking about electric cars, reducing carbon footprint and things like that. But on the dashboard in the electric car, we want AI. Now ask yourself, like, I mean, it seems ironical in a sense to say that, okay, on one hand we want all of these things where we want to nullify the carbon footprint, but on the other hand, there is a beast in the making in the back end, right? So obviously this is not a sustainable approach, not just sustainable from a literary perspective, sustainable also from an earth perspective, right? So whether is this the way to go, how can we bring smaller models where we are more respectful of the carbon footprint is a huge open issue at this point in time, right? So no very clear pathways at this point in time. As always has been, it's interesting to also see data as the opportunity now, right? So if you look at the entire neural network pipeline here, right? So our machine learning pipeline, you have data, you have an architecture or an SVM, whatever model you want to throw there, you have an output, right? I think that I was trying to look at the opportunities in each of these, right? So from an architecture perspective, the opportunity is probably looking at smaller architectures, and a lot of companies which are in the mobile and embedded space are now trying to see how do you do these architectures at a more architecture level, right? I'm not sure how many have heard of a company called Cerebras in the US, which is trying to see whether you can have neural networks in the architecture at the hardware level itself, right? Not really have to build something at a software layer on top of hardware, right? So there's a lot of talk about that. Data itself is an opportunity, right? So data has always been a hidden treasure, right? We all know that people say data is the new oil. How much curated labeled data you have is pretty much the limit of how well you can perform on a particular application domain in practice. And there's a lot of need for creation of data sets for the proverbial next billion of people, right? A lot of the data sets that are out there today correspond to the first billion of the developed world, right? So those are the data sets that are publicly available, right? So when many of you go to Kaggle and solve a problem, sometimes I say this, that we're probably solving some other country's problems, right? So because that's the data set that's out there on Kaggle, right? I know there are a lot of Indian data sets now growing, but it'll be great to have more and more data that come from realistic situations in developing and underdeveloped countries, so that those problems can be solved, right? So data remains to be a important treasure, and obviously there is a lot of newer data types that are emerging. People are talking about multimodality, where you try to have architectures that can solve vision and text together, vision, text and speech together, all of them, put them together and have architectures that can unite all of them, rather than have a separate model for NLP, a separate model sorry separate model for vision, so on and so forth, right? And I'm quite sure you all know what prompt engineering means, right? But in research perspectives, there is also what is prompt learning, right? Can you also update the prompt itself using backpropagation and bring that into the learning process of the model itself, right? So those are also dimensions that have come in. And the other aspect of looking at data towards AI as we go forward is all machine learning models today as we speak, I hope you'll agree with me, are data driven, right? You learn from data set, right? It's a little surprising that we don't consider domain knowledge in most of these models. I think there's somebody who works on healthcare, right? Let's say if any of you, and I have done this myself, right? Let's say you want to work on a healthcare project, what would you do? You go to a hospital nearby, see whether they have data sets of patients that they can share with you, do whatever documentation, NDAs, MOUs required to access that data, talk to the doctors to understand the problem a bit, bring that data over to your lab, right, or your organization, and start training models on that data to see what you can predict on that particular data set. Okay, this is what is typically done. But the same organization, the same doctor you spoke to has knowledge. They probably know that if a person has a certain blood group, they may be more inclined to have a particular disease, right? If they know these things, right? But we don't tell all of this to the model. We tell the model, you figure out it from data. We don't have a way of giving all of this to the model, right? I'm just giving a simple example of healthcare. There are many other domains where humans know the knowledge, right? So I'll give you few more examples a little later based on our work. Let's say I'm trying to predict, I hope many of you may know that, like I think in India it's a little nascent, but in the Western countries, college admissions are driven through ML models based on your SAT score, based on your performance, right? You can feed in all that data to machine learning models and they'll tell you what is the probability of getting different colleges in the country. Okay, it's already there, these things already exist. If a person gets a higher SAT score, or in India's context a JEE score, you know that the probability of better college always has to be higher. It's monotonic, right? It's monotonic. We know it, but we don't tell the model that, right? Now if the model learnt a non-monotonic function relationship between those two variables, we say if it gives the result we don't bother, but we actually know how it should behave. We're just not communicating that to the model, right? So how do you integrate domain knowledge into these kinds of models is a big open gap now at this point in time, right? So one thing I'm very sure, right in this room from three feedbacks, two of them spoke about two different domains, healthcare and agriculture, right? So should you just blindly use data and build models, or how do you bring domain knowledge into training these models is a very open question. I'm quite sure if I asked you, tell me in your course on machine learning or deep learning, who taught you how to integrate domain knowledge into your models? There's no such algorithm, right? There's no such algorithm that's taught to you. But clearly you know, especially for those of you with these domain knowledge, you know that it should be integrated in some way, right? I'll talk about it a little bit. I mean, we have some methods which we have developed for that. I'll talk about that a little later as we go. But that's an important opportunity to consider, right? So as AI is exploding in different domains, trying to understand how you can bring domain knowledge becomes very important. Also, now let's go to the output space of a neural network and see where things may go there, right? So let me take the example of computer vision more because I work in that area, right? But it could be true of NLP or other areas too. We started by solving the image classification problem a few years ago. Then we went into object detection. Then we went into semantic segmentation where we can label every pixel in an image. Right? Just observe the evolution is we have tried to solve more and more complex problems. Right? An obvious question then is what is the next complex problem we want to solve, right? So that's what we want to see, right? And I think this is an important point to consider, because I do feel that in a country like India, we generally follow the hype curves that happen around the world, right? We generally wait for a trend to emerge and then latch on to the trend. I think it's very important for us to think of what trends may come 3 years from now, and we be the leaders of that trend rather than follow somebody else's trend, right? So that's why probably some of these things, we need to catch a new trend before somebody else catches it and we just latch on to it, right? So I think these kinds of brainstorming, and some of these bets may not work, right? But that's what research is about, right? So taking that leap of faith and trying to see what happens. So let me tell you something interesting here, right? So to tell you what could go forward, right? How many of you know AlphaZero? Heard of AlphaZero? Right? Anyone heard of AlphaZero here? Okay. So what is AlphaZero? Sure. It's a chess playing system. Okay, it's developed by DeepMind before they bought Google actually, but before they got bought by Google. But yeah, it's Google's at this point in time. And in fact, it beats Stockfish by learning in just 4 hours and so on and so forth. And Stockfish is probably among the best computer playing software. So sorry, chess playing software. And that came about 2018 or something like that is when AlphaZero came. It was a sensation around the world. Like everybody was following it. There was news articles. In fact, if I'm right, the Time magazine had this as on its cover page or something like that. Right? It was a big thing. Right? I'm not sure how many of you are old enough, but how many of you heard of Deep Blue? Okay. Anyone? Okay. Do you know what? Correct, right? So, exactly. Deep Blue was the system developed in the late 90s by IBM and it played Kasparov and beat Kasparov at that point in time, right? Now, imagine I told you this. Now, answer me the question, then what did we as a community achieve in 20 years? We did this in 90s. Again, we did this in 2018, right? Same thing happened, right? But it became such a revolution when we talked about it in 2018. So, can you think and say what could have been different? We did the same thing 20 years ago, right? For those of us old enough, or probably if you followed history, you probably know that this news was there even at that time, right? Any thoughts as to, all right, yeah, it is right, okay, it was a expert system based approach. So what does it tell us? But still we just solved the same problem, right? So what do you think it tells us? Okay, valid point. It took a lot of domain knowledge, okay, got it, all right, okay. It was given a lot of chess games to learn from, and based on that it was developed, right? So it was given a lot of these games that are out there in the public to learn from those strategies and then propose a strategy, right? Anything else that you can see?
Was it reinforcement learning?
You could say so, right? Reinforcement learning was the methodology to achieve it, but I would still ask the question, used another technology to solve the same problem. What is great about it? Right? So as a civilization, you would hope that as we grow, we solve newer problems, right? I hope you'll agree with me. But then we solve the same problem. So what is there to really pride ourselves about it?
Maybe it was efficient or optimized.
Okay, partially right. Okay, any other answers?
It can be about how we can, the process that was followed to solve this problem, how we can use it to solve, say, another problem.
Okay, again partially right. Okay, again partially.
It's not just about chess, but it could also be applied for similar other games.
True, okay, that's a valid point, but I could have the similar argument to say that if the same people who developed Deep Blue went for other strategy games, they would have developed it. They could have done the same thing, right? So they could have done it too, right? But your answer has an intrinsic answer, right? So I'm trying to look for that. Okay, let me go to that, right? So there was a subtle difference, which is probably what you're trying to allude to, which is when Deep Blue was played, right? The system that was developed did not know what chess means, did not know what a black square, white square means, did not know what pieces mean. If you said like G6, H7, right, which is the way chess moves are written, right, then it would understand and go through that combinatorial space of possible moves and choose a move that could eventually give a good result, right. But AlphaZero on the other hand learnt what a black square is, learnt what a white square is, okay, learnt what a king is, queen is through vision, and then could also play the game, okay, which is why this could extend to other video games like Atari, things like that, because there you also have to understand the scene to be able to play the game, right. That tells us something very, very important as to how we have evolved over the last 20 years and where we may be going, right, is A cognitive psychology view of intelligence says that there is a process called perception, cognition, action, right? That's the way we process information. That's at least one of the most popular theories, okay? Where we first perceive, that's where I'm standing in this room. The first thing I do is I perceive the room, right? By perceive, what do I mean? I see the room. There are colors, there are some shapes, there are some edges, there are like some blobs around the room. That's perception, right? Then I cognize, right? It goes to my cortex. Then I realize, oh, there are people here. Okay, they're all looking at me. Okay, they're all nodding. They're doing something, right? So I cognize. Based on that, I act. What is my action I'm doing? I'm speaking, right? That I act. Now, based on the action, the perception changes, and it follows as a loop, right? It follows as a loop, right? So this is called as this is the PCA from cognitive psychology, not the PCA from machine learning, right? So now, what does that tell us, right? So now, can you look at this and tell me, what do you think we were solving between Deep Blue and AlphaZero? Now that I've told this, can you put things in context a little bit? Exactly. Perception has improved tremendously. In the 90s, we straight solved the cognition problem. We didn't bother about whether the chessboard can be perceived. We assume that somebody will feed us that information into that form, and I will only do the move manipulation. And somebody will actually move it on the board for me. The perception and action, we said somebody else will do it. I'll only have to do cognition. Okay. No wonder that did not take off to consumer applications, because without perception, cognition is of no use. Right. In the real world, if you don't perceive, there's nothing to cognize. So while we had solved a cognition part of the puzzle, we could not take it to the real world, because without the perception part of the puzzle, you cannot apply cognition. Right? If I told you, I'm going to block your eyes, now tell me what's happening in the room. I'm going to block all your senses. Okay? You cannot feel, you cannot touch, you cannot hear. Now tell me what's happening in the room. Obviously you cannot. Without perception, you cannot cognize, you cannot reason, right? But this is what we wanted systems to do for a while. And what did deep learning really revolutionize? Perception. Ask yourself, what are the kinds of problems deep learning has been really successful in, right? I'll again give the computer vision example. It can be similar in other domains. Image classification, object detection, semantic segmentation, all these it does very well, right? These are all perception tasks, right? These are all perception tasks. These are not cognition tasks, right? So what deep learning is really revolutionized in the last 10-15 years is the space of perception, right? Okay. Now, going back to the history of AI that I talked about, right? I said in the 70s, people started seeing alternate ways of doing AI, symbolic AI, logic, things like that. Now, it nicely fits into the puzzle. We can now bring the perception part of the pipeline from neural networks and bring logic in, right? Which is why everybody is now talking about explainability reasoning, because that is the next piece of the puzzle. Right. As a community, we have moved on from perception and are now talking, even without our knowledge, nobody has said this, but without our knowledge, we are actually talking about the cognition part of the puzzle now. 10 years ago, we were talking about how do I get better detection performance, how do I get better segmentation performance, but we've all moved on to talk about responsible AI, explainability, things like that, because we moved to the cognition part of the puzzle as a human civilization. Right? We've actually got there now, right? So which is interesting, right? It's interesting to see. And what we thought of as two facets of AI, right? I don't know if any of you had the chance to look at the history of AI. You'll actually see debates whether a history of AI is connectionist or symbolic or things like that. They're actually two parts of a pipeline rather than two different ways to approach the problem, right? Only thing is we did not know how to put them in sequence before, but now we're getting a better sense out of it, right? Now tell me what you think is coming up next. Action, right? Action, right? Now, what does that mean? Robotics, because if we can perceive well, I don't think we have solved the cognition problem, right? So the cognition problem is an ongoing effort, largely speaking, for the world at large. Perception largely solved, a lot of niche efforts still yet to happen, complex problems still yet to happen. But I think from a broad perspective, significantly solved. We are now in the cognition phase, right? The obvious next thing is, suppose in this room, I could put a camera, right? And it can not only perceive, it can exactly tell me what people are doing, thinking, intending, things like that. That's the cognition part of the puzzle. The next thing is, how do I manipulate the environment to change it? That's the obvious next thing that we'll talk about, right? How do you manipulate the environment? What does that mean? Things like robotics, things like agent-based systems. It's already happening. Copilot is manipulation, right? Copilot, I'm not sure how many of you know Copilot. So it's a coding help tool, right? So let me put it in that way, right? It's a way that can manipulate your environment. Now think that Copilot, you can have Copilots for everything. Imagine now that you wanted to book a railway ticket on IRCTC, you know that that the day of Tatkal, that 5 minutes, how tense it can become to catch that ticket. But you know what you do in that 5 minutes. How nice it would be to have a Copilot do, you know the exact sequence of things that you'll do. But you have to do it every time you have to book a ticket, right? Even say a flight ticket. You know the exact sequence of things you have to do, okay? But you have to do it every time. A Copilot can be very useful, right? A personal Copilot would be even more useful, who understands your wishes, your preferences, things like that. Do you see that coming? Perhaps, right? Perhaps, right? And all of these are systems that try to manipulate the environment, right? By manipulate, I mean act on the environment, not just perceive and cognize. Perceive and cognition would mean that somebody looks at the railway tickets and tell you this is the fare, now you decide. You do the actual booking. Doing the booking would actually become an agent-based system, an manipulation environment, right? So you can clearly see that's going to come, right? It seems evident, right? Obviously, there'll be regulatory things, there'll be pitfalls as we will struggle, we will come up with a method that doesn't work, all of that will happen, right? So, but you can probably get a sense of where we are going as an AI community, right? So, some things for thought again. Okay, one thing I'll talk about, which is also maybe the precursor to the next half of my talk, right? So, I'm roughly at the halfway mark, and this is going to be the precursor, is I'm also going to say that we have done machine learning wrong for the last 60-70 years, right? So that's what I said. I'm probably going to make it a little provocative. Let's see whether you all agree with me, right? So I hope you agree with me. The most standard ML paradigm that's been successful is supervised learning, right? I hope all of you agree with me on that, where you have some data, you feed it to a machine learning model, and it outputs a label. And for the model learning, you use different algorithms like neural networks, support vector machines. You use different kinds of algorithms to learn it, right? Now, just sit back and think. If you taught kids the same way from KG to PG, right? Sorry. That means you would be teaching maths as 2 plus 2 equals, choose between 4, 6, 9 and 13. And the kid has to choose and you finish the maths class. You teach every subject using MCQs. That's the way we have been teaching machines for the last 60-70 years, right? Agreed? Right? Because classification, cross entropy error, whatever loss function you choose is simply to see did they get the output right among the different options, which is MCQ, right? Do we agree with that approach for education, right? Since many of your students, if your teacher said, I don't worry about how, I'm not going to give any partial marks, I'll only look at a final answer, would we agree? Right? Probably not, right? But suddenly now, we want models to reason, we want models to explain, okay? We want models to be responsible, we want models to be fair. While for the last 60-70 years, the only thing we told it is your output is fine, right? The entire paradigm of learning, theory, application, everything is about that output, right? Even the fundamental formulations of machine learning start with let x comma y in supervised learning, right? Let x comma y be a tuple that's given to you where x is the data and y is the label, right? Which is effectively saying I don't care about anything in between, right? I only look at the x and the y, right? But now suddenly we've woken up and we want all of these things, right? So then what is the approach, right? So if obviously I'm criticizing this, then what should we do, right? So I'm not going to say this is the only approach, this is one plausible approach, right? So this is something that at least we have been working on in our research is currently the way supervised learning works is given an image, you give it to a machine learning model and it gets an output, say an image of a cat, you call it a cat, okay? That's how you train these machine learning models. Now, can we move to a setup where given an image to a machine learning model, the first thing you observe is there are pointy ears, there are whiskers, there are beady eyes, 4 legs, furry coat, and hence it is a cat, right? Now do you see that you reason and come up with an outcome, you are not going to tell the model just give me the outcome. So that's the title of my talk today, as how do you go from learning via prediction to learning via explanations. Right? I hope you agree with me that this is fundamental, right? We want kids to learn that way, right? We want students to learn that way, right? You don't want students to learn just using MCQs, right? We want them to be able to reason and come up with an answer. But then how do we go about imbibing this into machines is a very open problem, right? Okay, having said that we have done it wrong, I mean, was it really wrong? No, we needed that as a civilization, right, to get to this point, right? We needed that, right? There are parts of human intelligence where we don't reason. The perception part of human intelligence, we don't reason. If I'm walking on the street, I'm not reasoning, why is this brown? It's just brown, that's it, right? I'm not saying that, oh, they should have chosen this combination of colors and working out, okay, this is this combination of R, G and B and hence it's brown. I'm not doing all that calculation. It's brown, that's it, right? That's how I go. Even humans, we don't reason in the perception part of the puzzle. So it had a purpose, right? It had a purpose, but it's time now to go from learning via prediction to learning via explanations, right? I mean, I have a lot more thoughts about this, but I'll probably save it for the discussion phase as we go. And the nice thing about such an approach is that reliability and robustness come along free. If you learn via explanations, you know the model is reliable, it can explain its answer, right? Robustness comes for free. How many of you have heard about adversarial perturbations and adversarial robustness? Any of you heard about it? Okay. Adversarial perturbations and robustness are in, say, computer vision. People talk about it as, if I take an image of a cat and you change one pixel, just one pixel or like 5 pixels or something like that, many of the best performing neural network models today will start calling it some ostrich or something else, right? And it's a known phenomenon. Will all models do it for all images? No. There are certain images with certain perturbations, these things happen, right? If you could come up with a reasoning for that outcome, can the model do it? Not possible, right? If just a few pixels change, there is no way it can reason about the existence of these semantics while coming up with a completely different answer, right? So robustness comes for free when you learn via explanations, right? So we all know that that's something that we want education systems to move towards. Maybe we need to think about it from a machine learning perspective also, right, as we go forward. And this entire space of trustworthy AI are issues on deployment of these systems, right? So I think we briefly talked about it in the beginning, but responsible AI, safe AI, fair AI, explainable AI is all, when you deploy these AI systems, what are the opportunities in terms of research and contributions, I think remains an open area at this point. Okay, I think I'm exactly at the halfway mark, which is perfect. Maybe a good time to pause. And any questions, interactions, discussion, feel free to disagree with me. You can, I mean, this is meant to be a workshop, not a talk. So please do feel free to ask questions and share your thoughts. But just to let you know, the remaining half of the talk, I'll go a bit technical, right? So the last half was a little bit more high level, 20,000 feet view. But I'll go into some specific things that we have done in these directions though, right? So I will focus on explainability, but go a little bit into some of these things that they've done. Any questions or any thoughts from anything so far? Sure, yeah, very much, yeah. These are, as I said, this is not set in stone, right? So it's just my personal musings.
I mean, I'm no mean an expert in this area, but some parallels or some similarities I can see with healthcare is this, we have this, again, kind of debate that, we have this evidence-based medicine, which largely relies on data per se to drive decisions. So of course, evidence is all, mostly randomized control trials wherein you have group comparisons and all that. And then you have this experiential approach also, where you say that, a group of physicians who have worked in the field and cannot actually, give some hardcore data or something on it, but what they've seen and through experimentations, what they've learned, share and come together as a group of experts and share their thoughts on it. So what is parallel in this is that when we move from this, like the supervised learning paradigm that you told us about, like we give it a lot of data and then you tell that this is the relationship, please look at it. In the medical perspective, like this experience part, what I was talking about, the way we learn through experience is there is only limited set of questions we can answer and limited variables that we can process. And it is more of like anecdotal in the sense we go one-to-one with patient and that kind of an experience we build. But the other approach, the labeled approach, actually brings in a new dimension for us. In the sense, probably the field has not looked at. I mean, from the general problems, it is a little bit different in the sense that as a community, as a field, I don't think we have explored this empirical approach. That is, get this data, label data, and then see what are the patterns. So in that sense, I think this supervised paradigm also adds a lot. But again, data remains a huge challenge with this paradigm. But it does add a different perspective, which brings in a lot more value. But like you rightly said, even though it answers questions, we won't be trusting it because we don't understand it. So this approach, what you spoke about, is kind of very interesting because it brings best of both worlds, wherein you not only learn from the data, but as you learn from the data, you reason. So that, so it's like much more than what a single doctor or group of doctors can do at scale.
Right.
So that's what I just wanted to share.
Sure, absolutely. And what I think I'm trying to say is that we need a marriage of both of those approaches, right? So a healthy mix of both those approaches. So, I mean, we've also done some research in that space. Hopefully, I'll have the time to talk about it today too, right? So, any other thoughts? Any of you who do not agree with me, right? So, yeah, please.
They're getting confused due to missing some pixels in the images. So, are these missing pixels considered as noise? And are these handled due in the data pre-processing stage, or do you have some algorithms that handle this?
Sure, yeah. So, so it's a security risk. It's not noise risk. It's a security risk. So it's not just noise. It is noise, but it's somebody trying to willfully add noise to change the system, right? So you cannot change it in pre-processing, right? So let's say this building had a biometric system to enter, right? And let's say you were registered to come in and I was not registered. What I'll do is, if I know the machine learning model that's here, I'll take my image and I'll manipulate 2-3 pixels. Maybe I'll put, like, I can just dress up with a few dots here and there, and the model will get confused and think I'm you and I can enter the building now, right? So it's a security risk. So this is something, so there are methods for this. Those group of methods are called adversarially robust methods. So there are methods to handle it, but it's a cop and thief problem, right? It's a police and thief problem, where there are a group of people that are trying to break the system, there are a group of people that are trying to protect the system, and that battle remains, right, at this point in time, right? So, but if you're interested more, you can read up about adversarial robustness. Okay, there are papers and methods in that space for doing that. Sure. It's still open. Systems are still not robust. You can still break a system by changing images a little bit, and it will predict something completely different, right? If you search adversarial robustness, you'll still see, right? So I think things are slightly becoming better. There are methods, there are what is called adversarial learning to make systems more robust, but it costs a lot more, right? You have to try to imagine to see what could be the different variations of an image that could attack my model, and you train your model on those also. Right? So that's how you kind of you play around with that system, but obviously that's more cost to the system, right? So there's a trade-off. There are methods, but it's any security game is a constant police and thief kind of a game, right? So there's one group trying to hack, there's one group trying to protect. That remains, but things have stabilized at this point, is what I would say. Okay?
Excuse me, sir. Sir, can you go to the previous slide? So in that you explained that the program is trying to understand that whether it is a cat by reasoning, by it has 4 legs, whiskers, and body eyes.
Right.
Beady eyes, sorry.
Right.
So usually as a human in a kindergarten or LKG, UKG, during that time we have been shown images that this is a cat, this is a lion.
Correct.
And we are not learning in that sense that okay, it has 4 legs, so it might be a cat, so it is having a furry coat.
Right.
So if we are training this model in this way, will this model be able to learn that it can be a lion also?
Sure. Yeah.
It has also the same qualities.
Understood.
So how you will be able to achieve this?
Excellent question, right? Very good question. So I think for this, obviously, for kids, we don't test them on reasoning in LKG and UKG, right? So we are now talking about slightly higher grades where you test people on reasoning. Let's say a 3rd grade, 4th grade student, right? The same example that you gave, right? They may not be taught okay, that these are different parts of a cat and hence this is a cat, right? But they learn it because of so many kinds of experiences that they have in their life, that if you ask a third grade student, why did you call it a cat? They can go back and reason. They can go back and reason. Because of the way we are, because this is not the only image where you will see a pointy ear. You will see pointy ears in multiple things, right? At the end of the day, if you ask a third grade kid as to why do you call it a cat, they will say, they will give a reason. They will say it has 4 legs, it has a tail, it has a furry coat. They are capable of that reasoning. A model cannot do that because we never checked on it, right? It's very hard to compare apples to human learning, because human learning is very non-linear. What I mean by non-linear is we don't learn from one data set and learn one task. Today I am going to my school, in the afternoon I am going and playing with my friends, in the evening I am going to my grandma's house and learning some story, there a cat may come, right? So I am learning in a very, very non-linear way, right? And all of this knowledge is going back and forth, and our reasoning is getting reinforced through multiple experiences. So when we do that, although we don't teach about that cat in that way, we can backward reason. Kids can come back and say, I call it a cat because of this, this and this, right? Now, in this particular example, don't go too literally into this example, right? Obviously, when you call it a cat, you have to have some distinctive features of a cat, right? Then only you will call it a cat, right? Maybe I should have had one more attribute that says small. Then it won't be a lion, right? Then it won't be a lion, right? So, obviously, this is just an example, right? So, just don't follow this. Obviously, you want to get those, the key operating word, which I did not say so far, is intermediate semantics. That's the key operative word, right? So far, we always looked at only input and output of a model. But what we also need for reasoning, for any reasoning, we need intermediate semantics, right? Right now, you stopped and asked me this question, right? It's the intermediate semantics that I'm explaining to you now, right? If I wrote a problem on the board, right, and I took an equation and I wrote its solution, right? If you don't know how I arrived at, if I wrote the intermediate steps, you'll understand, right? The key to understanding is intermediate semantics, right? Let's take the example of ChatGPT, right? If ChatGPT solves a problem for you, okay, but it also gives you the intermediate semantics of how it arrived at the problem, you're actually convinced, right? The key operative word is intermediate semantics, right? As long as you find a way to teach that to a model, I'm saying it's okay. Right? However, right, if you tell me, no, I want to stick to standard machine learning, but I'll use some other approach to give its intermediate semantics, which is the way human learning works, right? Because our learning is not unidimensional. We get inputs from multiple ways. Fair enough, right? As long as a model gets intermediate semantics is probably the key here, right? Which is something we have never focused on over the last 60, 70 years of machine learning.
Like you gave that wonderful board example, as in, like if I interject and ask a question, you're able to reason it. Right. You have given the outlay, you have given that this is what it is, this is, we go from A to B, but then when somebody else asks you how, like the user asks the model how you went about it, then it tells like how did it go from A to B. Right. Now another part of it, same in the same setting, is can the model also ask a question to understand the problem better? Like, sure. Can that be boiled into the learning part?
Absolutely, right? I mean, so in a very loose sense, people call that setting of machine learning as active learning, but which is similar to this kind of a learning in a classroom is called active learning, even from education field, right? There's an active learning is a field in machine learning too, but active learning, the way it is used in machine learning today is, if I'm given 1 million data points, can a model decide which points it wants labels for? That's how active learning is defined in machine learning. Once again, we are only interested in the final semantic, not the intermediate semantic, right? The moment we have mechanisms, currently we don't have a mechanism for the model to query an intermediate semantic with you, right? We don't even have a mechanism for that, because the only thing we have told it is X and Y, nothing in between. The moment you start exposing the model to intermediate semantics, I think there's more opportunity to have that kind of a relationship, right? So obviously, yes.
So you talked about multimodal data type. So can we combine image, language and voice together? Is there a trend?
Yeah, I mean, the recent versions of ChatGPT, Gemini are all multimodal.
Yeah.
Right? They're all multimodal, right? So in fact, we're all going towards that. So yeah, it's already happened.
Okay.
I mean, it's already happened.
Yeah. So. If we introduce new data types, new data points, can we, you talked about earlier, so can we train, can we still the model is will be explainable?
I'm not sure if they're connected.
Mhm.
I think explainability is a different construct, right? Ideally, it should not depend on the data type that you're training the model with.
Yeah,
right?
if we
Ideally
introduce
speaking.
new classes to classify on.
Oh yeah, you
Yeah,
want it to
that's.
happen. You want it to happen. Obviously,
Haha.
you want it. See, that's exactly the reason why I'm saying that if intrinsically you train a model by learning via explanation, then you train for a new class, you learn to explain that also. Right? So that's why I'm saying that it's a paradigm change as to learn via explanation instead of learning via prediction. Right? The way we've all been doing machine learning, the way you all been taught machine learning, the way we all teach machine learning is we only look at it as supervised learning. So in which case you don't know how to explain the existing classes, or I mean it's not built into the model at least, right? So you can explain it using other methods. But when new classes come, you have to ask these kinds of questions. But if intrinsically you learn via explanations, obviously anything you do, you will explain, right? So that's how it will happen. I think there's one more question.
Hello, sir. So, to what extent should the model explain its reasoning? Because
Very valid
when we
point.
look at this image, we did not even consider the word small in this
Sure.
until he pointed out the
Absolutely.
differences between a cat and a lion.
Absolutely, very much. That's a very good question. But if you don't mind, I'm going to defer it to the last part of the talk today, because I have a slide exactly to answer that question. Right, and
Okay, sir.
I mean, I actually feel that is something that is missing today. But I'll talk about what that implies towards the end of this talk.
Okay, sir.
If I don't say it, if I don't answer your question at the end, please bring it back.
Okay, sir. And then second thing, it's slightly not a very professional question.
Sure. No problem.
So, what do you think about the Shagoth meme?
I actually don't know what it is.
There's a very famous meme regarding deep learning networks that it's actually Lovecraftian entity which we don't even understand anything, but it has a smiley face on it.
I see. Okay. Okay, that's a very deep question. So, in fact, there's a. I mean, I was part of some recent survey that was going on around the world. In fact, on there's a broader question there, which is about sentience, right? So, sentience is what separates AI from any other human beings. For that matter, many other things too, right? So, which is still an open question. Right? We still don't know whether AI. I mean, there is a thought as to can AI systems become sentient. I think that's a thought. I don't think we've got there yet, right? I don't think we've got there yet. So in that sense, it's still an inanimate object, right? So it doesn't have emotions or sentience as we speak. I think sentience is probably the key as to how things can change. And as things stand, we are not yet there. Right? We are not there. Okay, maybe in the interest of time, let's move forward. I know there's about 45 minutes left. So I do think I have more slides than what I can cover, but so I'm going to pick and choose a bit to see what to cover. Okay. So this is what I wanted to cover on a more technical front, but if any of you I'm going to leave the option to you to see what I should cover in the remaining 40 minutes or so. So as I promised in the beginning, the idea was to have one half of the talk today very broad and open, which we have kind of finished, and hopefully it was of some value. But the next half I wanted to go a little bit more technical, deeper equations and so on, right? So to probably all say how these things are achieved in practice, right? So it's easy to do this armchair criticism of what is going on, but what should we do in the real world to actually make this progress, right? So I wanted to go into that detail. So to that effect, I wanted to talk about some 3 of our recent papers that are aligned with what I've been talking about for the last 1 hour or so, which is about causal explainability, right? I will talk about what that means, but I wanted to talk about this 3-part paper, 3-part effort, research effort that we've had, where in the first effort, a paper that was published a few years ago, where we took a trained neural network model and tried to understand what causal relationships it learned, right? For those of you who don't know what causal means, I'll talk about that too, okay, just bear with it till then. But we tried to extract what causal explanations a trained neural network learned. For all practical purposes, people who have not done deep learning course, a trained machine learning model, that's all, right? In a second work, which was a couple of years ago, we asked the question that we have been discussing so far is, if I had domain knowledge, how can I integrate it inside a neural network, right? I'll talk about that too as we go. We already have a method for this at this point. And more recently, earlier this year, we also talk about what are called as indirect causal effects, right? So many times in the real world, one variable can cause some other variable, that variable can cause some other variable, right? But the way we learn machine learning, we assume, I hope all of you have done a basic machine learning course and you've heard of the IID assumption, right? What does IID stands for? Do any of you know what IID means? Okay, I hope in your machine learning course you've been exposed to it. It's an assumption on the data. Let me give you that. Yeah, identically, independently distributed, right? So that's a fundamental assumption in machine learning, right? Pretty much for all algorithms, all their theoretical guarantees hold under that assumption. The data is sampled in an identical way, in independently distributed way. We assume independence of the variables that are involved, right? That may not be true in the real world, right? Variables are related, right? So how do you model when variables become indirectly related is also something that we try to do more recently. Okay, so I'm going to talk about this three-part work. I also had some slides on high-level approaches, on existing approaches to explainability and so on and so forth, which I don't think I'll have the time to cover both. Which would you all prefer? I'm leaning towards doing this so to give you some tangible grounding of what we've been discussing, or do you all prefer more high-level views of explainability? Any preference? Okay, no preference. Okay, then I'll take the call, right? So I'll do this, and feel free to stop me. And if any of you want more details, I can always stay behind and ask questions, right? So I think we have spoken about this enough, but to probably bring back things to what the title of this talk is: why do we need explainability at all, right? So we've spoken about a lot of loose words as to where the field is going to go, but why do we really need explainability could be a fundamental question. So if you go back and characterize the machine learning applications we use, right? So let's not talk about special case users, talk about the general public, commoners like you and me. Think about applications of machine learning that you use, right? Can you list out any where you think you use machine learning on a daily basis? Okay, Google Translate and translation. Okay, anything else? Any other things that, sorry? Okay, Google Lens. Okay, point out and find out what's the object in front of you. Okay, anything else? Okay, search, Google search. Okay, product recommendation, right? Movie recommendation on Netflix. So whether tweet recommendation to you, so on and so forth, right? So all of these are things that machine learning, you use machine learning for it, or your spam filter, right? Spam filter, all of these are machine learning applications, right? So if you just abstracted out a bit and asked, what is the questions that we are trying to answer with these machine learning applications? Some questions that would come up will be, what is the product relevant to the user? What is the sentiment of this tweet? What are the objects in this image? These are the kinds of questions to answer which we use machine learning today. Okay, agreed? Okay, and if you abstract it out, this becomes, what is X? Is the core question we try to use machine learning for, where X could change based on context and applications. Okay. And this is useful when the cost of a bad decision is low, right? Ask yourself the places where all you use machine learning on a daily basis. These are all places where a cost of a bad decision is low, right? Okay, you get a bad product recommendation, a bad movie recommendation, you lose 500 rupees, you lose 1000 rupees, it's okay. You don't lose a life, you don't use an arm or a leg. Ask yourself, how many people use Amazon to buy a house, right? The moment the cost becomes high, I'll rather consult my friends, family and all of them. I will not simply go with a blind recommendation system, right? House recommendation systems don't exist, right? So it's too valuable to just blindly follow a computer based recommendation system, right? Another example I can give you, which is even more powerful, is, I mean, all of us went through a global pandemic, right? Just very, very recently, right? It was a global thing, right? And AI was a trending topic even during that time. I hope all of you will agree with me on that, right? And contactless technologies were the need of the hour at that point in time, right? But how many hospitals where when you went in, they would take your blood sample, use AI and say you will not get COVID or you don't have COVID, and it'll tell you go back home. How many hospitals did this? Right? Ideally we should have. It's the best contactless technology you can have. Nobody needs to wear a mask. You just go, a robotic system tells you, you can go back home. It was a global pandemic, one of the trending technologies around the world, but we still didn't use it at a time when we needed it to save lives. Right? Why? Because the cost of a bad decision is high. Even if you have a model which is 99% accurate, during the period of COVID, I wouldn't have gone to that model, because if I'm in that 1% of failures, it's a matter of life and death. The moment the cost becomes high, we are not willing to trust ML models anymore, right? This is a very, very important thing to keep in mind, that what do we want to do? We want to go towards, just a minute. Okay, yeah, so I thought I had one more slide on this. What do we want to do? We want to go towards systems where it is not only what is X, but also Y is X. Okay. If we had deployed systems which could say the risk of COVID, but could also tell you why it gave the decision, okay, then you would trust it, because if you're not convinced with the why, you can take a second opinion. Right? You can take a second opinion, right? But if your why is convincing to you, it's fine and fair enough, right? The why becomes very, very important the moment you move to risk sensitive applications. Okay. For a large part, machine learning is not yet percolated risk sensitive applications. For a large part, right? There are obviously exceptions, but not yet percolated risk sensitive applications from an end-to-end implementation perspective, right? In a healthcare setup, yes, if you go to a CT scan, you see the different areas are highlighted. That's machine learning in the background, but that's for a subsystem. Decision is not based on that. A radiologist makes the decision, right? So, but this is not the only thing. There are also regulations that necessitate explainability, right? I'm not sure how many of you know, but by the way, Europe is perhaps the world leader in regulations for AI at this point in time, right? The rest of the world is far behind. Europe passed this clause as part of its GDPR Act. I'm not sure how many of you know GDPR. GDPR stands for General Data Protection Regulation. This happened way back in 2018, where it included this clause that says a business using personal data for automated processing must be able to explain how the system makes decisions, right? If a bank uses machine learning to decide whether a customer gets loan, if the customer goes back and asks the bank, why did I not get a loan? The bank has to answer. The bank cannot say, I used a machine learning model to come up with the answer, right? So, is this a first world problem? Is it Europe's problem? Not really, right? Remember that machine learning software in a Deutsche Bank in Germany could have been developed by an Infosys or a TCS or a Cognizant, right? Which means people sitting here, we are a very globally connected economy, which means engineers here are responsible for these systems, right? So, which means that these kinds of regulations necessitate explainability to be a part of your machine learning model. It's not an afterthought, it has to be part of the deployment, right? So, there's obviously one reason to go beyond where we are today, but regulations also require us to have explainable models, right? So, just keep that in mind in most risk sensitive situations. I'm not sure how many of you have seen Niti Aayog's document on responsible AI. Niti Aayog, which is India's planning commission, has an entire strategy document on responsible AI where it talks a lot about explainability, transparency, accountability also, right? So, the first question that somebody could ask is,
I talked to my friend,
Right.
and that too, it's a personal call.
sure,
During that time, my opinions and my things, whatever we discuss, similar kind of post, similar kind of shots come up by the evening itself. If I was having
Right,
that discussion in the morning, the similar kind of this post will come up.
right.
So isn't that dangerous? Isn't that
Absolutely.
making people into a bipolar situation? If I'm in a if I have a left side opinion, I'll be completely shifted to left side, and if I have a right opinion, I will completely shifted into the right
Absolutely.
side.
Very much, yeah. I mean, this is part of the conversation around the world. I think that's what I was saying, that I think there was a session yesterday on responsible and safe AI. I think this is a huge problem. This is significantly debated in the communities around the world at this point. It's a huge problem. Completely agree on this, right? So, regulations are still evolving in this space, right? It's very, very hard. Even for lawmakers, it's not simple to come up with regulations. Since you brought up this question, right, Europe has been significantly ahead in having regulations to be very strict. For the rest of the world, including India, I think it's hard to come up with regulations because they don't want regulations to stifle innovation, right? So, you see now, a very simple takeaway is from tomorrow, nobody should use this technology on YouTube or on the phone. If you say that, new technology is very hard to develop because there are positive uses also of these kind of things, right? So, the challenge is about regulation versus stifling innovation, and that's not an easy balance, right? So, I think at this point, if you say we are as a technology community confused about which side to lean, right? Including the big companies around the world, right? So, it's a very valid problem. I don't think we have a very clear decision at this point. The con is this, right? It's not about an obvious answer is we must regulate, but the problem is the moment you regulate, you'll stifle innovation, right? And for a country like India, do you want to do it? Do you not want to do it? Becomes very hard, right? The moment you say that, okay, such systems should not exist, then startups that are trying to come up with new AI technologies, like, see, remember, that's also the pathway to commercialization, mass implementation, right? If you stop that, then it's hard to also have startups that come up in this space, right? So that's the difficult conversation in this space.
Sir, I think the same situation came up when people started discussing about nuclear power plant, nuclear energy.
Absolutely, people
They were
relate
saying that
exactly.
we need to make nuclear
Absolutely.
powered cars and all.
Sure,
But
sure.
finally, these things were contained into this all,
Correct, correct, yeah.
more in a very
So we are
secure
going through
manner.
the discussion phase in the AI community at this point in time. People, you are very right about people. In fact, compare AI a lot to the nuclear era, right? So, but we have not yet found a resolution yet, right? Because AI's use cases are more near term. Nuclear has had a very long life term to realize its consumer use cases. AI's use cases are being realized very quickly, right? So that has made it harder to make these decisions. Right? But you're very right about those problems at this point. Okay, let's come back to explainability. So an obvious question somebody could ask is, can machine learning models already do explainability? Not really. A lot of the most explainable models like linear regression and decision tree, which are the most explainable models, unfortunately don't perform the best in terms of accuracy. On the other hand, models like neural networks and support vector machines, which are probably better in terms of accuracy, are not the most explainable, right? So there's a trade-off here between interpretability and accuracy. So ideally we want to go towards models, going back to the title of the talk, towards learning via explanations. You want models that can get high accuracy as well as give you good interpretability. That's what we want to go towards, right? So clearly we don't have that space yet at this point. So I think I'm going to skip this in the interest of time, right? So I know we have about half an hour. I wanted to talk about some of our efforts that could be relevant to the discussion. But I will point, if any of you are interested in knowing the literature around explainability, please look up these kinds of links. There is a link called XAI tutorial, followed by the year, right? So I think they did it up to 2022 if I'm right. I forget the exact year they stopped. But XAI tutorial 2021 is the one I picked this image from. But if you go to these websites, it gives you a very wide treatment of different explainability methods, right? So I maybe will just give you a 2-minute preview to what explainability methods mean, and I'll then go on from here. So I think I'll skip some of these in the interest of time. Let me give a high level view of the explainability landscape, right? So there have been many methods. The entire space of explainability started in 2015 when an organization called DARPA, many of you may have heard of DARPA. DARPA stands for Defense Advanced Research Projects Agency. They are also known for their invention of the internet, right? So they only created the first version of the internet. So they launched a significant effort on explainability of AI systems in 2015. So that was quite early at that point. That's what led to the proliferation of efforts in explainable AI, and personally I have been working on this from 2016, 2017 myself. And over the last 8-9 years there have been so many different methods that have come up. Most of the methods are what are called as post hoc methods, right? That is, you've already trained a machine learning model, now you want to explain, right? Because we only had models that learn via prediction, not learn via explanation. You already have trained models, now how do I add a layer around it which can explain its decisions, right? So that's what most of the methods did. And the broad ideas are somewhat like this. I'm not going to go into specific details. There was one idea called LIME, which is very popular, is deployed in the industry today, where the broad idea is, after you trained a model, when an image or a document or some data comes in, you perturb that image. You perturb that image and give different variants of that image. Now see which variant, when you give, drops the confidence of that output significantly. Right? Then you know which part of the image was most responsible for that outcome given that particular model. Right? So that's what LIME did. So that's one idea of doing explainability. There have also been the most common approaches, especially in deep learning, has been what are called gradient based approaches to explainability. What does that mean? Right? I'll try to give a quick background. All of you know a neural network, hopefully, right? Even hopefully people who did machine learning also know at least what a neural network is. If you have a trained neural network, its weights are frozen of the neural network. Then you can take the gradient of the output with respect to the input. Right? You can do chain rule to do dou y by dou x. For training a neural network, you were probably taught that you must do dou error by dou w, right, to learn the weight updates. But you can also do dou y or dou e, where e is the error function, with respect to dou x, which means I have a trained model with fixed weights. If I want to know why did my model call this a cat, I have to take the cat neuron and set its value to be 1 and do a gradient of that output to the input layer. Then I'll get to know which pixels were responsible for that cat neuron to fire the most. This is the most simplest way people do explainability, right? I put it in very simple terms. There are like at least 5-6 variants of this approach itself which are used in practice, right? How do they vary? How do you compute the gradient? People keep changing different formulas, right? So there's an approach called GradCam. We ourselves had an approach called GradCam++, which is also used a lot by the people around the world. So there's also something called integrated gradient. There's also something called smooth gradient. As you can see, the methods are all very similar. They just vary in how do you compute the gradient. Okay, I'm not going to go into each of them. But there's also another direction. The another way of computing explainability is through what are called Shapley values. Okay, Shapley values are a game theoretic concept, but the way they are used in explainability is, this is the formula that's used in Shapley values. The way they are used in explainability is, suppose I want to find out, right? So let's say the T20 World Cup is starting, right? So let's say I want to find out what is the importance of Virat Kohli to the Indian cricket team, right? So let's say that's what I want to find. The Shapley value way of doing it is take, let me see here, S, right? So yeah, I, okay, I would be Virat Kohli here, okay, and then take every team with Virat Kohli and without Virat Kohli, right? I is Virat Kohli, so V of S union I minus V of S. The value, the value function is a function that you define for a particular problem. You could say winning a game is what is a value of a particular player. So how many times with Virat Kohli did we win, and how many times without him we won? Okay. Now you have to take a combinatorial expansion of various possibilities of teams where Virat Kohli was there or not there, right? Including 2-player teams, 3-player teams, 4-player teams. In a cricket match with 2 players, when Virat Kohli was there, how many times we won and how many times did we not win? You'll do it in a combinatorial sense to decide what is the value of Virat Kohli to the team, right? This is what is replicated. This is a game theoretic concept, as you can see, right? This is what is replicated for understanding which variable in a vector is responsible for a particular outcome of a machine learning model. I've trained the machine learning model. The value function here would become, sorry, I'm not able to erase it. The value function here would become getting a classification prediction correct or some things like that, right? So how many times with a particular pixel did I get the classification prediction correct, and how many times did I not get it correct will tell you the importance of that pixel towards getting that class correctly, right? So this is another way of explaining a model, right? I hope you get a sense, right, in an intuitive way. So these are different approaches to explainability, right? So again, I'm going to stay with this level. If you're interested, please do go through the link that I shared, XAI tutorial. You'll get to know more details, and I'll also share a few references at the end, right? But in the remaining 20 minutes or so, I'm going to share a little bit about some of our efforts in this direction as to how do you go toward learning via explanation, right? So rather than learn via prediction. So as I mentioned, I think we've been looking at explainability for a few years now, and over this journey, initially we looked at a lot of post hoc methods for explainability. Okay, then we realized that while that is useful, that's not the right way to go forward. You need what are called as anti-hoc methods to explainability, where you learn via explanations. That explanation is not an afterthought that you put after you train the model. It is something that you have to think of while training the model itself. And we've also been looking at a causal approach to explainability in all of this, right? So I'm going to cover the second part quickly in the next 50 to 20 minutes, where I'll also talk about the anti-hoc explainability, right, within the causal sense. Let me go into detail. So one of our earliest efforts in explainability was way back in 2017-18, where we came up with a method called GradCam++. I mean, as an academic, right, so it was nice to see that this method that we proposed has been used. It continues to be used by people around the world. People use this to explain COVID-19 diagnosis. People use it to explain defective cells in solar arrays. People have used it for cancer prediction, pathogens in histograms, leaf counting, so on and so forth, right? So it's nice to see when an academic effort actually leads to somebody using it in practice. But after we did this work in 2018, right, so many people were asking us this question. People were trying out different things, and we saw some results such as these, right, where you see here when people used our approach on COVID-19 CT scans. This was the original CT scan. GradCam++, which was our approach, showed that this region here, right, where you see red heat map, is the part of the CT scan why this person is COVID positive, right? So that's what it told, right? So it's not only predicting it to be positive, it's explaining which part of the image is the reason why I'm calling this to be positive, right? So that a radiologist who's involved can take an informed decision, okay? But we actually found that papers were showing that the causal explanation for this is just one small part of the CT scan, not an entire area, right? So we realized that there may be an importance to going beyond correlation based explanations to causing based explanations, right? I'll give you one more example. People use that method to find defective cells in solar arrays, right? It's very common. These days, you know that solar farms are everywhere. To find out whether a solar farm is working properly or not, people use drones or imagery to get a picture of an entire solar farm. And then you use machine learning to find out which are these defective arrays which need to be replaced or serviced, okay? But just telling an array is defective is one thing. But if you can explain and say, I'm saying this because look at that part that looks very different from the remaining, is very useful to a service engineer, right? So that's where the explainability part came in here. But once again, we found that a causal thing to say that this is the exact cause for this problem would be very, very useful for people in the on the field, right? So that's what led us to think about explainability from a cause perspective, but I'll go a little bit more into detail on this. So in our first effort in 2019, we tried to take study that if you took a trained neural network model, can you find out what causal explanations it has learnt, right? So I missed one small part here. The word that people use in the explainability space for this is called attribution. Okay, attribution simply means that how much did an input variable attribute towards an outcome, an output variable. That's called attribution, which is nothing but explanation, right? So if I said, if I had 10 input attributes and I said, I want to explain my decision, okay, then if I tell that, okay, suppose I take a hospital data, right? I want to find out why I predicted a particular patient to have a high risk of heart disease, okay? If I can say that I'm saying this because this person has been smoking for the last 10 years or 20 years or something like that, that's one way of explaining, okay? Not the only way of explaining, one way of explaining, right? So you try to see how much does an input variable attribute towards the particular output. That's called attribution, and attribution is the most popular way of doing explanations, right? You can do attribution at a word level to a document or outcome in NLP. You can do attribution at a pixel level to an outcome in computer vision, or you can do attribute at a variable level in tabular kind of data like hospital data or things like that. The core problem is attribution, right, across all of these data types. So what we tried to do in this work is try to see what kind of causal attributions does a neural network learn when you train a neural network. Okay, that's the first work that we had done. So I'll come to the subsequent parts later, right? So, but to go there, I probably first need to talk about how many of you know what causation means or what causal means? Okay, all right, okay, let me very briefly explain it, right? So in statistics, there's a very popular, concepts to differentiate between correlation and what is called causation, right? So very popular example people give is this one. There are many such graphs on the internet, but this is a statistics of ice cream sales and shark attacks in a certain Bay Area in the world, and you can see that both of them peak in summer, right? So if you see this data, you see that both of them are high in summer, obviously, right? Now, if at all both these data come into a data set about that city, the next time you eat an ice cream, the model is going to predict shark attack probability is high, right? Because that's how correlations work. That's how we train machine learning models today, right? If these two things happen to be a part of a data set, if you know that the presence of one always indicates a high presence of the other, if one is present, you'll obviously say the next thing may happen. Okay, that's how machine learning works today, right? Clearly, as you can see, this is correlation. This is not causation, right? Maybe I'll talk a little bit more into detail in a couple of slides from now. So the idea is, how do you bring these kind of causal, as you can see now, for explainability, causal is very important, right? If I just explained, I'll maybe give a few more examples as we go, right? I would have loved to cover these things. Let's see, we have, can I spill over by 5-10 minutes? Would that be okay? Is that okay? Okay, so let me walk through this example. I think this will give you the intuition for, since many of you don't know causality, I think I should quickly give you this, right? Okay, then I should switch back a bit. I'm sorry if you saw the slide. Okay, so let's take this example here. So let's assume that, let's consider COVID-19 when it was going on, right? Let's say there were two vaccines available, A or B, right? Even in India, we had two vaccines, right? A or B. And let's say there are two other variables, which is the condition of a patient and finally the outcome, right? Condition of the patient could have been mild or severe, and the final outcome could have been fatal, mortality, right? Whether the person was alive or dead. Let's now say that a certain newspaper published this data at that point in time, saying that vaccine A has 16% mortality rate, vaccine B has 19% mortality rate. Which one would you choose? You see this in the news and now you have to choose which vaccine to take. Which one would you choose? B, the one with higher death rate? A, right? Obvious choice, right? Because it has a lower mortality rate. Mortality is death rate, right? So, the one with lower mortality rate. So, that is what you would choose, right? But if I expanded this table, okay, I now say, now let the last column is the same as this one, right? Now, I simply expand this table and tell you how the vaccine worked for mild symptom patients and severe symptom patients. Okay. The Simpson's paradox in this is, in both mild cases and severe cases, vaccine B had the lower mortality rate, but then the overall mortality of B is higher. Why do you think this happened? Okay, this is called as a paradox. In both cases, the lower mortality rate was actually B, but overall the mortality rate of A was lower. Why do you think this happened? I'm sorry? Okay, a sampling bias, right? Vaccine B was applied more to more severe symptom patients, right? So that is the reason why it had an overall mortality rate which was a bit on the higher side. But now if somebody showed you this, which treatment would you choose? B now, right? B now, right? So I mean, these things could have happened, right? Even as I hope these could have been very realistic scenarios that could have happened, right? Even now it depends. It depends on what's the true causal graph. If it happens that the condition caused both the treatment and the outcome, you could go for treatment B. But if the treatment itself caused the condition and the outcome, A is still a better choice. It depends upon what the true causal graph is. In which way were the variables actually cause to each other. Okay, that's the reason why causality becomes important, right? So in this scenario, these mild and severe conditions are called confounders, right? So if you didn't know them, you would have thought that there's a certain connection between vaccine and outcome, but the moment you know them, you get a different sense. Why treatment A is better here? Yeah, because if I say that the condition does not cause the treatment, in which case A is better, right? So see, if in case when I know the condition resulted in the treatment and the outcome, then treatment B is better, okay? But if I know that the treatment itself caused the condition, okay, then A is better. A would be better in this particular case, right? If treatment is, it depends on the causal graph, right? It depends on how actually involved. So when I said mild and severe, one thing I did not tell you is that, was this mild and severe after they took the vaccine or before they took the vaccine? I did not tell you that, right? The second graph assumes that the condition was measured after the treatment was taken, right? Obviously, in this case, it's the most blatant answer that B would be the right choice, but I'm saying that it can depend on the causal graph, right? How things actually work in the causal graph. So that's why the causal graph, knowing how variables are causally related, becomes very, very useful, especially when you explain, right? I'll give you a few more examples as we go. So this was the first work. It was joint work with some of our students, Aditya, Piyushi and Anirban, and to the best of our knowledge, this was the first causal work on explainability around the world, right? So that's what we had done in 2019. To understand this, I have to introduce a few technical terms. As I said, I did want to go somewhat technical, so but I know I have limited time, but I'll try to cover this in some level of detail at least, okay? So the fundamentals of causality come from what is called as the structural causal model, okay? Structural causal model is the model based on which data is actually generated, any data. Even as I stand in front of you and you're seeing me, this image that falls on your retina is generated. Light falls from light sources on me and I am reflecting that light off, it falls on your retina and you're generating this, and a particular image is coming of me based on the lighting position, the ambient lighting in this room, so on and so forth, right? Whether I mean there's any glossy materials that are reflecting off on me, so on and so forth, right? There are many parameters that decide what image you're seeing. Similarly, any data generated in the real world has a causal process, right? that causal process is captured by what is called as a structural causal model. There are a few variables, they are connected as a graph, and how they are connected within their graph is written as two equations, right? x1 is a function of x3, x2 is a function of x1, x3 is a function of only noise, then x4 is a function of x2, x3 and some noise, right? All the n's stand for some exogenous noise, right? Some outside noise that could just enter the system, which we cannot monitor or measure. This is called as a structural causal model, and that's the fundamental premise of the study of causality. A second notion which I need to explain is the notion of what is called an intervention. Okay? In causality, an intervention means that if I change, let's take these structural equations, if I now set the value of x1 to be 2, I am intervening in the system and saying this variable will only have this value. Obviously, based on that, the rest of the variables will assume particular values. This is called as an intervention, right? I am intervening. It's like, since some of you have healthcare, it's like saying that when you're doing a randomized control trial, if you say this patient has to take this drug, I want to do that intervention and see what happens. It's the same notion here, right? It's the same notion here. It's an intervention, and that based on that, the rest of the variables assume their values. Okay. And the third term I need to introduce is the term of the confounder. A confounder is a term which influences two different variables causally, due to which you think there is a relationship between those two variables. Going back to the shark and ice cream example, there are ice cream sales and shark attacks. You think they are correlated, but both of them have a common confounder called higher temperature, right? The moment you know that these two things are not causally related. But if you didn't know that, you assume that these two things are causally related, right? That's the notion of a confounder. It's a confounder is simply another variable in your system. That's all, right? It's just called a confounder because it confounds. Now, what we try to do, I do think I have to speed up, so let me see how much I can cover. But I'm going to take one running example to explain our three works, right? So I'll stay slightly at a high level. Let's see how this works. So let me take this running example of predicting heart disease risk from a certain healthcare data set, right? So please don't question me on the clinical side of this. I'm not a clinician. So, but this is just an example to showcase this, right? So let's say there are lots of variables like family history, age, BMI, education, diet, birth month, smoking, LDL cholesterol, blood pressure, so on and so forth. Based on these, I have to predict heart disease risk for a given person. Let's say that's how the system is. Obviously, we know that there is a true causal graph, right? Family history can affect BMI, diet can influence BMI, BMI influences heart disease risk, birth month has no causal effect on heart disease risk, right? There's a certain causal graph here, right? Again, don't question me on the correctness of this causal graph. This is just an example to say that there's a certain causal graph, okay? Now, if you apply any existing machine learning explainability method, right? I talked about a few explainability methods. This is an example of taking a random forest, training it on the UZI heart disease data set, and applying an explainability method that's used in practice. It tells that the highest attribution is for resting blood pressure. It tells that blood pressure was the highest attribution for heart disease risk. Okay. Clearly, it may not be causal. Okay. It's possible that a higher BMI caused a high blood pressure and a higher heart disease risk. And you assumed, just like how we saw shark attacks and ice cream, heart disease risk and blood pressure may just be two variables for which there was a common confounder, which is BMI, right? Which clearly you can see machine learning systems, even explainability methods that are used today, don't capture. If you told a patient your blood pressure is the reason why your heart disease is high, go fix it and come, what would the patient do? I hope you realize it's not causal. I have to find out something else that will reduce my blood pressure. I ideally need to tell the patient what is that causal attribute, okay? What is that causal explanation through which they can reduce their heart disease risk? And that's where causal explanations become very, very useful, okay? That's what we work on in this work. So just to give you a machine learning perspective to why this is important, here is an example of taking three setups: X causes Y, X is caused by Y, Z causes X and Y. X and Y are not directly causal to each other. And if you write out these three setups in equations and create data sets, you'll actually find that the three data sets are exactly the same. Okay. What does this tell you? that when you are given a training data distribution to train a machine learning model, you actually don't know which causal distribution it can represent, because the same distribution could come from multiple causal graphs. Here's an example. I mean, if any of you want, you can take these equations and run and see, right? The same distribution, same joint distribution, right? Which is, I hope you agree with me that this is supervised data, x and y, both are present. Okay. If you take a same data and train a machine learning model, it could have come from any causal model. X could have caused y could have caused x, z could have caused x and y. An obvious counter question you can ask me now is, why should I care if it works? That's an obvious question, right? The challenge is, when you now set x equals 3, you now get test data. The distributions completely change now. When you intervene and set x equals 3, you can again look at the equations here, you can try it out later if you like, the distributions change now. Which means if you had really modeled the true causal graph, you would have generalized well. If you had not modeled the true causal graph, you may not generalize well. Okay, that's why causality is important in machine learning, especially when you want to generalize well. Okay, now let me come to how we actually go about doing this in our work. I'm probably going to skim through this. I don't think I'll have the time to do every equation now, but I'll again be happy to stay behind to answer any questions, right? So what we do is, as I said, our goal was, if you take a trained neural network model, how do we understand what causal explanations it has learnt, right? That was our first approach's goal. So we take a neural network, okay, and then we first of all show that the neural network can be looked at as a structural causal model itself, because it has input variables, it has output variables, and the bipartite graph of a neural network is itself like a graph, where the input variables cause the output variables, right? By default, we have assumed that those arrows exist. Even if in the true causal graph, a particular B variable did not cause a certain output variable, the way we have connected a neural network, we have assumed that it causes, right? That there is a relationship between those two. So we consider this to be a structural causal model, and from literature in causality, we define this quantity called the average causal effect. Okay? The average causal effect is given by this quantity here, which is the expectation of y given that you intervene, right? So this do thing that you see is known as interventions, the intervention that I just spoke about a few minutes ago. Given that you intervene and set a certain xi to be alpha, right? If you set a certain xi to be alpha, that is one variable, you set it to a particular value, you want to see what is the expectation of y across all other variables outputs, right? So that's what you try to do here, minus expectation of y given that you intervene your xi to some baseline reference value. That's what we refer to as a baseline. That is, I'm trying to see, if I want to find the causal effect of blood pressure on the outcome, I want to see if I intervene and set my blood pressure to say 150 by 100, and the expectation comes by saying that all other variables I'll allow it to be anything, blood group can be anything, age can be anything, only blood pressure I change. How did the risk of heart disease change when the blood pressure was 120 by 80 and when the blood pressure was 150 by 100? That tells you the causal effect of blood pressure on heart disease risk, right? So these are first principles definitions of causal effects, right? So the challenge that we had in this work was, how do you compute this for a neural network? Okay, that's all we did. Okay, that's all we did. So the next few slides I'm going to talk about that. So we had to compute this quantity for a trained neural network. So in this, basically there are only two terms to compute, this term and this term. The first term is called as interventional expectation, which when you expand becomes an integral. Okay, this expectation term becomes an integral because it's an expectation. Okay, it will become an integral. The second term is simply, what we do is, if you had domain knowledge, for example, you know what reference blood pressure is, you can set that to be your intervention and study the same effect. If you didn't have domain knowledge, we simply take the expectation of expectations to choose that baseline value, right? That becomes like the average of average values, right? Something like that, loosely speaking. Okay, these are the two terms that we have to compute the causal attribution of a variable inside a neural network. So I'm going to very quickly skim over the math here. So what we do here is, to compute this integral, we consider the Taylor series expansion of the causal function that we want to estimate, and by intervening on xi and taking expectation, this simplifies. Only the second order term will remain, the first order term won't remain. I think I'll skip some of these details here. And we also show that I mean, when we use this kind of an approach, at some point in time, you will get the Hessian of the neural network in one of these terms. The second derivative is the Hessian of the neural network, which can be very, very difficult to compute, right? The first derivative itself takes time. The second derivative of a neural network is even more time taking, right? So instead of that, we use some linear algebra formula to show that you can compute this entire Hessian vector product in 3 forward passes of the neural network. You don't need to do anything else. This entire Hessian vector product here, we actually compute it through just 3 forward passes of a neural network, right? So that's some of the math playing around that we do to make this more compute this more efficiently, right? The causal attribution. That's the main contribution of this work, and we also show that we could use this approach for not just standard neural networks, but also for other neural networks like recurrent neural networks and all of that. Okay, but let me show you some results to show what this means, right? So I hope all of you may have heard of the IRIS dataset. It's a very popular dataset in the UCI repository. So we train a neural network on this, and then we try to study the causal attribution of different variables. Let me just explain one of these graphs to you. What this shows you is for the iris setosa class, we want to study what is the causal attribution of each of the variables in the iris dataset: sepal length, sepal width, petal width. Right? Those are the 4 attributes that you have in that dataset. We want to study what is the causal attribution at each intervention value. Right? When the sepal length is a particular value, what is the causal effect that it will be iris setosa class? When the petal width is a particular value, what is the causal effect? It will be the iris setosa class. Okay, that's what we are measuring in these graphs. Similarly, we measure it for iris versicolor, iris virginica, so on and so forth. And when we did this work, there was not too many ways to validate how correct this is, right? So what we did was we built a decision tree based on the values that we see in the causal effect, right? Now, by looking at these graphs, I can say that if petal width is less than 0.29, it must be iris setosa class. Then if petal width is less than 0.69, okay, you can see it in the iris versicolor class. You can see that this range is when you get the iris versicolor class, and in this range when petal width is high is when you get the iris virginica class. We write that as a decision tree, and we find that using that decision tree, we are actually able to match the accuracy of pretty much all decision trees that we implemented in this setting, right? So that was a way we could validate that the way we could get the causal effect was useful. But we also did some real world studies. We worked with Honeywell at this point in time, where we try to look at flight landings, right? So that is another risk sensitive settings where people use machine learning, right? Automation of flight controls and things like that, where we took flight landing and we used our method to be able to study what is the causal explanation when a flight lands badly. Okay, just to let you know, when I did this project, I got to know that whenever a flight lands badly, has a bumpy landing or things like that, a pilot has to file a report, okay, and 75% of the times it's never fixed, okay, because no support engineer has the time to figure out what really failed, right? Because there are too many sensors and parts in a flight, they really are not able to fix it. Okay, so we were trying to see, can you causally identify what really caused the bad landing? That's what we were trying to do in this case. So I won't get into specifics here, but what we found using our method matched the FDR report, and even the aircraft engineer experts that were part of our collaboration agreed with what the causal attributions provided by our method stood for. If you're interested more in this work, you can probably look at our code and the paper that's publicly available, but that's what we tried to do in this work. The core takeaway was we came up with a way of, given a trained neural network, how do you understand what causal explanations that trained neural network learnt. Okay, that's what we tried to do in that particular work. I think I'm going to present the second work in which I think is the more interesting work. So I'll just take 5 minutes for that, and then I will conclude. The third work, maybe I'll leave it for you to read. The second work was a work that we did a couple of years ago, which could be of interest to the idea of learning via explanation that I was talking about, right? So we tried to ask the question that in many domains you already have some knowledge. How do you ensure that when you train itself, you try to ensure that the neural network model will definitely respect that known causal domain knowledge? Okay, that's what we try to do here. Let me motivate it first, right? So going back to the same example that I had a few slides ago, we have this heart disease risk example. We already know from randomized control trials, for those of you who don't know causality, randomized control trials which are done in clinical domain are considered the gold standard for causality, right? Which means you keep 2 groups of people who are exactly the same in characteristics, okay, largely speaking. You give one group a placebo medicine or something like that, and you give another group a real drug, right, and then see which group really comes through, right. So that's a common thing that is done in randomized control trials, and that's considered the gold standard for causal knowledge. There have been many such causal studies that have been done in clinical literature and documented. These have been done for decades together now. For example, we know that body mass index has a U-shaped relationship on heart disease risk. A very low body mass index is bad, and a healthy body mass index is say between 18 and 25 or something like that, and a high body mass index is also bad for health, right. It has a U-shaped relationship, right. It's not just BMI, right. Similarly, we know that age versus heart disease risk is a known relationship. Number of cigarettes per day to heart disease risk is a known relationship. Okay, cholesterol versus heart disease risk, these studies have all been held for this, right. So when we now train a model, machine learning model, to predict heart disease risk, don't you think we should incorporate this domain knowledge? Imagine we are now training it using hospital data without even telling the model that if a person smokes a lot, they may be at higher risk. It's known. You should say that whatever you learn, ensure that the relationship between the explanation or the attribution between your smoking variable and your heart disease variable should be monotonically increasing. It's something we should do, right? It's known knowledge. You don't even need to talk to a doctor for this, perhaps, right? It's known knowledge, right? So, but how do we bring these into neural networks is what we try to do in this particular work, right? So let me get into that detail now. So it need not be just I'm giving the example of heart disease risk, but there could be many other cases, right? As I mentioned, in college admission scores, there could be a monotonic relationship between a score and a college admission prediction. A fairness constraint, right? So if I'm trying to predict beauty from an image, I should not be looking at skin color, right? If I'm trying to give a loan, I should not be looking at race and gender, right? Or there could be many other kinds of shapes. It could be a U-shaped relationship, J-shaped relationship. All of these are documented in literature already, right? The question is, how do you integrate that and tell that to a neural network while learning itself, learning via explanation, okay? So to do that, we introduce something called causal regularization with domain priors, right? So we want to train a neural network. We are given a causal domain prior where we know a known relationship between an input and an output variable, and in this setting we assume that only for some variables you will have a known relationship. For many other variables you may not have, and those you learn however you want. It's like telling that I go to a hospital and I get 100 variables. I'm going to use that 100 dimensional data set to train my machine learning model. The doctor may give me inputs only 2 variables because that's all they know, right? Many other variables, maybe there are no conclusive studies. For those 2 variables, you maintain what the doctor said. For the remaining 98 variables, let the model do whatever it wants, because we don't have conclusive knowledge anyway. That's our approach, okay? That's what we try to do. We call this approach as causal regularization. Okay, this can get a little heavy math, but I won't go into the details. But when you go into depths of causality literature, I talked about causal effect a few slides ago. I talked about average causal effect of I had an interventional expectation minus baseline, okay? That causal effect has many layers. There is something called direct effect and indirect effect. When a variable directly impacts another variable, we call that direct effect. When a variable impacts a variable through another variable, you call that indirect effect. And together we put the two as total effect. Total effect equals indirect effect plus direct effect, okay? Now, as you can see in this example, BMI has a direct effect on heart disease risk. Family history has an indirect effect on heart disease risk, due to which BMI has a total effect on heart disease risk. Right? There are 3 things here, right? There are 3 things that can happen, okay? So what we do in this work, okay, I think in fact, yeah, there's one more layer here, is that even direct effect has 2 kinds called natural direct effect and controlled direct effect, okay? I'm not going to go into that level now. But what we do in this work is to show that given direct effects or total effects, we can use our method to include that while training a neural network, okay? So in the third work, which I may not have time to present today, we show that we can also control indirect effects in our neural network, okay? That I'll talk about briefly. So I think I'm going to skip some of the math details. If you're interested, you can go through the paper, but we show firstly that a neural network is identifiable. Identifiable in causality literature means that given statistical data, you can make out causal relationship. It's not possible in all scenarios. The example would be the shark attack and ice cream that I said. In that scenario, you cannot make out the difference between statistics and causal relationship. The scenarios in which you can identify causal relationships from statistical data, you call those variables to be identifiable in causality, right? So that's the notion of identifiability.
Family and all. Instead of doing that, why don't we take the circumference of the arteries?
You can.
Or
That's why I
instead
said
of
don't
doing
ask
that,
me. This is just an example. This is just an illustrative example, right? So this is not complete.
So
you can take that very much.
then do we need to do this equation if we are having that much
yes,
precise variables?
See, there's no guarantee. First, okay, let's say for a particular disease, do you know exactly which variables you should take from the hospital?
No, by seeing the body, if I don't, what if?
No, but you may need family history.
Okay, what if I don't smoke? My family history is also good.
But
I
you
am
need
a
those
minor.
variables. You need those variables.
Yeah, what if I'm a minor?
Sure, you need. I'm saying that you need those variables. I'm actually saying
Yeah,
that those
so
are the reasons why you need those variables.
We can get those by taking blood sample or something. We can find the amount of sulfate accumulation or
Sure,
what.
you need those variables. All I'm saying is you are questioning on the variables that should be considered. I'm saying this is just an example. Whatever variables you consider, there can be direct effects, there can be indirect effects, there may be no effect. You cannot say that upfront, right? It's very hard to say that upfront. In a particular domain, if you know exactly which variables to choose, by all means, do it.
Yeah,
That's
so
all.
if we have an expert on that domain, so I think most of the work will be.
No, not at all.
No?
Not at all. I mean, tell me that obviously experts in the world exist. Are we saying that experts in the world don't exist? That means all healthcare problems using machine learning should be solved as of today. You should go to a hospital, doctor will tell you take only these 3 variables, the rest of the data I gave, totally delete it, use these 3 variables to predict. No, we don't have such models. Because there are many other factors, right? It's not just one, you cannot, I mean, see, I said there may be smoking, there could be family history, each of those are variables. You cannot case by case, when you're training a machine learning model, your approach is you're giving it all the possible variables and asking it to correlate them and find a predictive outcome. You are not saying that I am not going to give it all 100 variables, I'll give it only 2 variables. I know remaining variables it doesn't need. We don't do that, right? We don't do that and we may not be able to do that either. Maybe there are very, very specific applications. Okay, let me back up a bit to answer your question. When is machine learning useful? Machine learning is useful when you do not know the relationship between input and output variables. If you know that there are 2 input variables and these 2 input variables cause this outcome, I know it upfront. You don't need machine learning, just apply that rule and solve the problem. It's like telling, suppose I give you the data points of f of x equals sin x, right? And now I'll give you a new data point. Do you need to do machine learning to predict? Given x, I'll apply sin x and get the answer. Why do I need machine learning to, I don't need to get 1000 data points of x values, sin x values, train a machine learning model and predict. I can apply the function. Machine learning is used when you don't know that relationship. When you know that relationship, machine learning itself is not required. Only when you don't know the relationship, machine learning comes into the picture, right? Now there we are talking about how can we handle these kinds of uncertainties. Right? If you know that these 2 variables are the only thing I need to consider, circumference of artery, these 2, with this I can always predict, you don't use machine learning at all. You directly use the rule and finish the problem there. Right? Machine learning comes into the picture only when you don't understand the relationship between input and output, right? So that's important to keep in mind. So, but wherever you use machine learning, these things become important, right? So that's all I'm trying to say, right? Because there are many variables you actually don't know how they relate to each other and you want to now try to see where there is causal effect, where there is indirect effect, where there is direct effect, so on and so forth, right? So that's what you want to try to see. Okay, coming back to this. So what we do in this work is, as I said, we want to do causal regularization, right? So I'll come to the main algorithm. We also theoretically prove that this algorithm holds. I'm not going to get into that, but I'll come to the algorithm, which is actually very simple to implement. The way the algorithm works is there's just one simple regularization term that you have to add to the loss function. Okay, whatever loss function you use to train a neural network, cross entropy loss, regression loss, okay, whatever loss function you use, just add one term to the loss function. What is the term doing? The term is saying, if you look at this particular term here, if you look at this subtraction, you're taking the domain prior, you're taking the gradient of the domain prior and matching it to the Jacobian of the neural network. Jacobian of the neural network is the matrix of all first derivatives. Okay, you are trying to match the gradient of the domain prior and the Jacobian of the neural network. Very simple, makes it very intuitive too, right? But we actually theoretically show that if you do this approach, it actually maintains the causal effect in the domain prior and for the output trained neural network. Okay, we theoretically show that this will actually hold in practice. So it's a very, very simple implementation in terms of what you have to do while you train the neural network, but then we can theoretically show that this will maintain the domain prior's causal effect and the actual causal effect of the trained neural network model. Okay, let me actually show you a few results, and I think I'll stop there for today. But okay, this is a heart disease data set. This is just the same example that we spoke about here. Let me show you this example. So this was our approach on using a neural network on the UCI heart disease data set, and we tried to study the intervention of cholesterol on predicting heart disease to be high. Okay, that's what we are trying to see. So we know from ground truth that GT stands for ground truth. That means we know that cholesterol has a monotonic relationship, right? Higher cholesterol has a monotonic relationship on heart disease risk, and that's what is the red curve there. When we train a neural network using standard approaches, you actually get the green curve here, which simply states, green curve stands for ERM. ERM stands for empirical risk minimization. You may have heard that in your machine learning course. Okay, that's the standard way to train, is called empirical risk minimization. You can see the green curve there, which actually seems to say that cholesterol is almost independent of the outcome. That's what the model seems to have learnt when you train a neural network using a data set, right? But you see that when we use our approach, where we regularize and also add our loss, the blue curve using our approach matches the ground truth. So not only is it, and you can see the accuracies are also not, we do well on accuracies too, right? Which means we are getting the same performance as a neural network, but now we are respecting what is common knowledge here. That higher cholesterol will lead to higher heart disease in this network. If this network was asked to explain, it will maintain that monotonicity in its explanation, which a standard neural network may not be able to do, right? As you can see with the green curve here. Okay, I'll show you a few more examples. Okay, this is another data set called AutoMPG, where we study this on displacement, on whether the miles per gallon. Let me actually show you some interesting ones. Okay, this is another one, which is called the MERA dataset, which is an environmental dataset, where we take the intervention on latitude variable on total precipitation. You see that the effect should be red. Ground truth says that there is a, as you go higher up in latitude, there's a certain relationship. After some time, it falls down. The ERM model, which is green, does not follow this relationship. Using our approach, which is blue, we actually come closer to the ground truth. I'll show you the most interesting one is this one, right? Is we now trained our, use this approach on what is called as the recidivism dataset. Okay, this is a fairness dataset. Recidivism stands for, it's a dataset that has records of criminals, whether they will recommit the crime. Recidivism stands for, in the next 1 or 2 years, will they recommit the crime? Okay, this is a dataset very popularly used for studying fairness in the US scenario. You can see here that if you keep increasing the amount of African American in a particular sample, you can see that the standard ERM model, which is standard training a neural network, keeps going, the recidivism keeps going higher and higher as African American increases, which tells that the model is heavily biased towards the African American race. Okay, while we know everybody is talking about, we want a flat curve here. We want this system not to be biased based on race. We want a flat line here, and you see that using our approach, we get close to a flat line. Right? You can see a similar thing, that if you intervene on Asian, you see that the ERM model has actually a negative relationship on recidivism. The more Asian a person is, the less the person is likely to commit a crime. Once again, a bias based on race. We ideally want the model not to be biased on race, and you can see our blue curve actually become independent of race, right? So you can see that fairness becomes a special case of learning via explanation, because if you say, you give me any explanation, don't give me gender as an explanation for why you gave a loan to a person, then the model has to ignore gender while learning its model, an algorithm has to ignore gender while learning that model, right? And that directly results in gender fairness in a particular scenario, right? So that's an example of an algorithm that we came up with for learning via explanation, right? So I think I'm going to stop there. More recently, we also did some work on how do you also capture indirect effects in a neural network. What if it happens, going back to this example, what if it happens that family history affects BMI and then BMI affects heart disease risk? Now, how do I tell the model that family history has a relationship on heart disease risk, or for example, education has a effect on heart disease risk, right? If anybody had told you that a person with a higher degree has lesser possibilities of heart disease risk. You'll ask me why, right? But education could influence diet, diet could influence BMI, and BMI could influence heart disease risk. There could be an indirect effect, right? Now, how do you tell a neural network about this? So, we came up with a new paper to also try to model these kinds of things in a neural network to maintain explanations even in indirect scenarios. So, if you're interested, you can look at our work on this. But I think I've already gone well past time. I think I should conclude here. But there are many other things we've also been exploring in the area of explainability. We have been looking at the notion of explaining from memory. Should reasoning always be intermediate semantics is a question, right? That's what I said earlier. Sometimes we explain via memory. Suppose a radiologist was asked to explain, why are you saying this particular chest X-ray means COVID positive? One is a radiologist could explain to say, look at that mass on that X-ray, I think it's because of that, right? Another thing a radiologist could do is, I remember a patient 2 years ago who had the same characteristics, who had blood group the same, everything else the same. Let's pull up that case and see what happened, and that person turned out to be COVID positive, and I could conclude based on that, right? So, humans, we also explain by memory, right, from cases, right? How do you bring that into neural networks is something that we are actively working on. We are also looking at concept-based models in computer vision to do that intermediate semantics. When you call it a cat, you have those intermediate semantics of furry coat, beady eyes, things like that, right? So, how do you bring that into the equation is something that we are doing. We have some ongoing work on how do you bring differentiable logic into neural networks, right? Reasoning is not always and, right? So, going back to some of the questions of around the cat, right? I said a furry coat and beady eyes and 4 legs and something is a cat. Reasoning is more logic. The negation of an attribute could also mean that something is present, right? Logic is far broader than just an and condition or an or condition. How do you bring that into a neural network in its layers is also something that we have actively going on at this point. We are also looking at the direction of what is called actionable explanations, right? Actionable explanations are explanations where, suppose I did not get a loan, right? I go to a bank and the bank tells me, and the bank gives me an explanation. The explanation is it's because of my gender, I did not get a loan, right? This is correct, the bank is absolved, legally the bank is right, but it's not useful to me, I cannot change my gender overnight, right? What can I do? So, I'll go back to the bank and say, give me an actionable explanation, don't tell me this. Then the bank may come back and say, okay, gender was the first reason, the next reason was your credit score, that's why you did not get a loan, okay? Now, this is an actionable explanation, but now again, maybe my credit score today was 600. Should I make it 610 to get a loan? Should I make it 750 to get a loan? Should I make it 800 to get a loan? What should I take it to? It becomes important, right? So, that's something that we are working on now as to how do you do actionable explanations. So, one recent work which we have put out to, it's available online, is we have been doing this for human post correction. So, suppose I have a camera in front of me and I want to learn to play cricket or tennis or do yoga at home, right? And I am doing a particular pose. I want the camera to tell me whether I got that pose right and give me an actionable explanation as to why I got it wrong. Suppose I am doing a particular pose and the model tells me your right elbow is not bending enough, that's why I am saying that your pose is not right. Now I know what to do, right? So, these are actionable explanations in practice, right? So, that's also something that we are working on at this point. Now, the last couple of slides and the question that I did not answer to you in the beginning, hopefully I remembered it, so I'll come back to it now, is at the end of the day, if you look at where explainability is today, right? So, I spoke about various things I think in the last hour and beyond too, and the elephant in the room in explainability is that it is an elephant itself, and it's like the elephant that's felt by 5 blind people where everyone feels it's a different thing. Explainability is something like that, right? A business owner thinks it's a particular thing, a data scientist thinks it's a particular thing, an IT ops person thinks it's a particular thing, an auditor and a regulator thinks it's a particular thing, okay, a customer support agent thinks it's a particular thing. So, I think it's very hard to know, explainability is a very subjective term, right? It's very hard to objectify it, right, and say it is exactly this. For a large part, the machine learning community has looked at explanation as attribution, which variable attributes what to the outcome. But that may not be the case, it may depend on who the user on the other end is. Even this session, I would speak differently if I am speaking to a KG kid versus all of you versus a peer researcher of mine. I'll have a completely different context if it's a peer researcher of mine, right? So, we give different explanations to different people based on who's on the other side of the coin, right? That comes to my last point, which I'm going to stop with, which I think should answer the question, is while if you see machine learning and AI, right, it's a revolution of automation, if you agree with me. The revolution of automation, this is not the first time we are doing it. The most recent one was the programming revolution, where we had an automation in terms of software development. The software development revolution has gone through an entire well-defined process of software development. How many CS students here? You probably have heard of the waterfall model and agile model and things like that, where you have a very well-defined process for software development, right? You start with user requirement specification, you have to complete a document, you have to have use cases, things like that. Only the third or fourth step is actually programming. Until then, you only gather requirements and go back and forth to actually freeze on those things. Then only you come to programming. You're not done yet. Then you have to do validation, you have to do test case analysis, then only you finally deploy, right? Machine learning is a way of automation where we have not yet developed this process. Right? We have now, the way we go about machine learning is get a data set, start working on a machine learning model. No user requirement specifications, no trying to say what the model should do or how the model should give the output, all of that is not done, right? With topics like explainability, fairness, responsible, safe AI, I think it's highly important to have a well-defined process for development of machine learning models, where the first step has to be user requirement specifications, which is something we don't do today, right? Now, going back to the question of what does the user want? Some person may want small to be the answer of a cat, some person may not want small to be the answer of a cat. Let the user say so. In software, we have a user requirement specification before we go into development. In machine learning, that has not yet gone through that rigorous specification of that process. I think it's high time now for the community to actually have that process in mind, so that the inputs and the outputs of the machine learning model are participative in nature, where people define what they want out of a machine learning model. Then explainability can have objective evaluation. Right? If a user tells me that this is the way I want the model to output the prediction, this is the way I want the model to output the explanation, here are a few case studies on sample test cases on how I want the output. Now I know what to do. Now I know how I should build my model, and ideally I should not build my model until that user specification is frozen, which is the way software development is done. We don't do that for machine learning, and it's time we have to do that for machine learning, especially when we talk about subjective things like explainability. Right? I'll stop there. If you want more resources on explainability, these are some of the links that I also mentioned. You can look at this XAI tutorial link, and there's also a very nice book online by a person called Christopher Molnar. If you just search interpretable ML book, you'll actually find a link. It's a public open online book which talks about different methods for explainability, so on, if you want to read more about it. Okay, I'll stop there. Just thanks to always my students, alumni, collaborators, and all the funding sources that have supported our research. I'll stay there. Sorry for going significantly over time. Sorry about that, but I hope this was of some value to those of you who attended. Happy to stay behind to discuss, but I'll stop here.